Dear participants, let's wait for 2 to 3 more minutes, then we can start. Hannah madam, you can start, madam.
Okay. Dear participants, welcome to the evening session number 7 on day 4. Today, we are going to have a session titled on solar panel design. It's going to be conducted by Mr. Dilip. I would like to give a short introduction about Mr. Dilip. He has completed his BE in Electrical and Electronics Engineering from Gausia College of Engineering, Ramnagara. And followed by that, he has completed his MTech in Computer Application and Industrial Drives from Oxford College of Engineering, Bengaluru. He is currently pursuing his PhD in Electrical and Electronics Engineering in Faculty of Engineering and Technology, JAIN deemed to be University. So he has conducted various technical training programs for various industries like Bosch, Schneider, Snedgen, and AT India Auto Parts Limited. So today he is going to conduct the session on the topic solar panel design. Over to you, sir. Dilip, sir.
Thank you for the introduction, Dr. Anna, madam. So, 1 minute, I will share my slide.
Dilip, it is visible.
One minute, sir. Sir, is my screen visible, sir?
No, sir. Now it is visible.
And could you help? Where should I see my screen? I'm just I can see the participant actually. But Dr. Kishore, sir,
Yeah, tell me.
where should I check my screen actually slides?
Yeah,
I just
yeah, slides are not moving. Please check with the movement of the slides.
yes, sir, slides, but the screen which I seeing the participant screen, sir. How can I go to the my slide section?
No, you can leave. You can see. Actually, it will be in the another window. Okay, you can go to
Okay.
another window and you can do your work. That's all. It will come here automatically.
Is it visible, sir?
Yes, it's moving
It's
also.
changing.
Yeah, it's changing also. Solar panel design has come now.
Okay, thank you,
Go
sir.
on,
Thank
go
you
on.
so much, sir.
Go to second one. Go to third one. Second, third. Yeah, it's coming. Fine,
Okay.
fantastic.
Thank you, sir.
Yeah, thank you. Thank you.
So, so good evening, everyone.
No, again, it's
So,
not
for,
coming. Dilip, check once. Huh. Yes, go to slide mode, full screen or slide mode, whatever it may be.
1 minute.
Yeah, that one.
Okay. Okay, I thank you. First of all, I thank you AICTE, and also I thank you Faculty of Engineering and Technology JAIN deemed to be university for organizing this ATAL online faculty development program and also faculty development program on power electronics application in microgrid using artificial intelligence. And especially I thank to the Department of Electrical and Electronics Engineering, Faculty of FET JAIN deemed to be university, and I personally thank you to Dr. Yelleraisen sir, HOD of EEE, and also the program coordinator, Dr. Kishore Kumar sir. So today 7 session. So from past 1 to 6 session is done very good. So I learned many things in mainly the inverter technology in the renewable energy. So today's session is mainly of solar panel design. So solar panel design, and these are the today outline of contents. So we learn about introduction of solar PV module and PV cell arrangement and off-grid and on-grid PV system, and how to choose the solar PV panel for the load application, and also how to choose the PV system for the domestic application, and a simple bar diagram of a PV module, and tilt angle or orientation of the solar panel, and what are the earthing or grounding system for the solar panel, and MPPT model, and also some simulation for PV module. So solar power. So before I start this solar power, so from past decade, like in 2015, a Paris climate deal has happened in Paris, France. So in that climate deal, we had an agreement in INDC. So India has pledged that we are moving from the fossil based fuel cells in a generation of electricity to a non-fossil fuels based fuel cell for the generation of electricity. From this time, so the power generation, that is renewable energy, become more and more topic. And also today the India already in a international platform, that it organized the International Solar Alliance back in 2016 only with France. So this is the world platform, so that already more than 120 countries are joined for the development of the solar energy. Okay, so this development, as lot of research is going in the solar panel design and also other renewable energy. Okay, so when whenever the solar power will come, so we need to mainly harvest the power of the sun, because from that sun we are getting the solar, that is renewable energy, solar energy. From this harvesting, we have mainly different technique or different methods for the harvesting of the solar power. So what are the different harvesting method? Mainly we have solar thermal method or chemical solar method of harvesting, and also solar photovoltaic harvesting. So what are the things generally solar thermal or
Excuse me,
chemical solar?
are you in which slide?
Sir, changing the slide, sir, it's not moving.
Yeah, it's not moving. Even slideshow has not come. So can you make it into full screen mode?
Okay, sir, one minute, sir.
Yeah. Yeah, now it is good. Please change the slides once. Let us check. Yeah, it's moving now. It's moving now. Okay.
Okay, thank you, sir.
Thank you so much.
So methods of harvesting. Mainly we have the three methods of generally harvesting we are used in an industrial technique. So solar thermal power method of harvesting, the chemical solar method of harvesting, and also solar photovoltaic harvesting. So solar thermal technology, so technique generally. So this is the solar thermal harvesting power technique. So in here, the solar thermal technology is nothing but it's a kind of mirror, that is heliostates. So these are the type of mirror and these are the heliostates. Okay, from this heliostates, it receives the solar power from the sun, and all the power is reflected. Okay, all the powers is reflected in a concentrated single point, which is receiver. From this receiver, when all power is reflected in a one point, sudden temperature will rise in the receiver. So simply it is a principal work of a steam turbine. So after the steam turbine process, this steam will generate and the turbine will convert into mechanical energy into the electrical energy. So in the solar thermal, same, there will be heliostats will be there. It acts as a mirror. So whenever the sunlight falls on this mirror, and it will be directed in a single point, that is receiver. So in receiver, due to high heat, so whenever the feed water will come and it will go to the steam drum, then the turbine. This turbine generally converts the mechanical energy into the electrical energy. So in India, there are mainly many solar thermal harvesting is there. So I will quote to, in India, Godavari Green Energy Limited has built a solar thermal plant in Rajasthan, which is 50 megawatt, and even the mega solar plant which is in Anantapur, it is also 50 megawatts. So these two generally are solar thermal method of harvesting in India. So this is the solar thermal harvesting. So in solar thermal harvesting, so mirrors will be there and it will be reflected in a single point. So another method of harvesting is nothing but what? Chemical solar harvesting. In chemical solar harvesting, it is a similar process of concentrated. Sir, is my slides changing?
Yes, sir.
Thank you, sir. So in chemical solar method harvesting, it is a similar process where the concentrated power at a one point. See, the concentrated power will be in a one point, and through mirror technology, from this heat will be transferred to this chemical reactor, and this will react based on the heat available in the chamber, and this chemical react will convert the solar fuel, that is fuel nothing but here they were using the hydrogen fuel. So this fuel will fit to the fuel stack, okay, or cell stack. So this cell stack convert the hydrogen energy into the electrical energy. So this is the another method of harvesting the solar power. So last method, generally this type of solar PV method, generally they were using in many application areas. So in PV method, we know the sunlight will reach the panel, and the panel will convert what? Electrical energy into the, generally panel will convert solar energy into the electrical energy, and it will feed to the AC load and also DC load. So in India, the biggest, the largest solar PV park, which is located in Rajasthan, which is of 14,000 acre, and it will generate 2,245 megawatt of power. So that is Badla solar plant in Rajasthan, which is the largest solar park in India, which are 14,000 acres and generate up to 2,245 megawatt. So let us know about the basics of what is cell. Okay. So generally we know this cell will be made up of silicon material. So this silicon material will be doped so that whenever it will be doped in a aluminum or phosphorus, so it will create a N-type material and P-type material. Okay, the N-type material will be always will be placed upon the upper side or near the face of the sun, because the N-type material we have the more electrons. Whenever the electrons will get energized, it will move from N-type to P, and whenever the load will be connected, so load may be anything, bulb or even motors. So this is how the solar cell will work. So solar cell contains what? N-type material and P-type. Between there will be PN junction, dielectric junction. So this is how it represents. So this is the equivalent circuit of the solar PV cell. So N-type and P-type, whenever the irradiation or solar, whenever the light reaches, it acts as a source. Okay. So within the cell, there are two types already told, that is N-type and P-type. So this is the solar PV cell. So in this is the solar single PV cell. Okay, whenever the combination of solar PV cell, it is called as what? Solar PV module. Means combination means, so more than the cell, single cell. Suppose in this module, so in a row and column, it has a what? 6 and 12. So totally it has what? 72 cells. Okay, the combination of PV cells is nothing but what? Is nothing but solar PV module. Okay, and the combination of solar PV module is nothing but what? Solar PV panels. Okay, so and also the combination of solar PV panels is nothing but what? Solar PV arrays. So that what we call solar park. So solar park contains what? Solar park contains combination of panels, PV panels. So combination of PV panels contain combination of module. Combination of module consists of what? Solar PV cells. So this is the how the solar cells, solar module, solar PV panels, and solar array is there. Okay. So next thing is how the panel design will happen. So generally, this is the solar cell. So this is the solar cell. In solar cell, it has a coating, that is encapsulant coating, and above the encapsulant coating, there will be glass will be there, then frame will be there. The coating, encapsulant coating will be upper side and the lower side, and the glass, and below that back sheet will be there and junction will be there. See, this glass is there, right? This glass is a non-reflective, means almost less reflective. It's not like zero reflective, it's almost less reflective. Whenever the reflective almost like generally not more than 5%, means whatever the sun rays will come in this glass, it won't reflect back. So it will pass into the encapsulant, and this encapsulant will help to absorb the solar rays in the solar cells, and these solar cells will help to convert the solar energy into the electrical energy. So this is the how the solar panel arrangement will be there. So example, I took the solar one data shift of the Eldora, that is Vikram Solar. So I am not promoting any company, but for example, I'm taking 72 cells. Means 72 cells already told in a row and column 6 and 12 will be there. That is what one a single module. And this is the watt will be there, right? So this is the maximum watt, that is 315 to 345. Means 72 a single cell will generate 0.6 or 0.5, generally depend upon the silicon material. So one silicon material will generate 0.5, one silicon material will generate 0.6. Depend upon the silicon material, the watt will be generated. So if we take the cell, but each energy manufacturer follow their own standard. So Vikram Solar, what I'm data sheet I took, they have the different silicon content that have the maximum wattage of 335 or 340 like that, and it is a 72 cells. Even some other manufacturer use the different silicon metal, maybe it will be less or it will be more, but it will be near. It's not like more margin, it will be a like near the margin. Means suppose if it is as a 72 cells, then if you multiply in a point, means one single cell is generating how much? 0.6 watt voltage. Means 72 into 0.6, it will be how much? It will be near to 43 or 44 voltage. Means in a single module cell, it is generating nearly the 45 voltage, or nearly to the 7 amps maximum ampere. So again, so generally what the solar panel generally depends upon the material already told. So different manufacturer will use the different material. Example, in a market we have polycrystalline material, monocrystalline material, and the thin film material. So let us see what are the this different silicon material. Suppose why we generally use the silicon material? Because it acts as like a photovoltaic diode generally. Okay, it absorbs the power from the sunlight and it will convert generally. So this different three types of polycrystalline, monocrystalline, thin film, they have the different efficiency and they have the different cost. Example, in polycrystalline, monocrystalline, generally this mainly they will used in the industrial application. In polycrystalline, the efficiency compared to the monocrystalline will be less. So this polycrystalline will be efficiency like this, not the battery efficiency, this is the panel. So it will be 15 to 70% efficiency, and we can easily identify this is the polycrystalline how? By the color. So the color of the polycrystalline will be blue in color, and the color of the monocrystalline will be black in color. So here, this is the expensive compared to the polycrystalline. Means polycrystalline is efficiency compared to the cost will be more. Means cost is less, but if compared to the efficiency of monocrystalline, less will be there. And In monocrystalline, it's in black in color. It is made of pure silicon. See, already told, depend on the silicon material, it will vary. Depend upon the silicon material. And also, if the same manufacturer using the monocrystalline, but the silicon material will be different, then they can't achieve the efficiency of 20%. That will be vary for some percentage. But in pure silicon, if they use for the monocrystalline, definitely the efficiency will be 20% more, and it will be most expensive also. Okay, and it is black in color. Another one is thin film. So thin film generally they use for the solar power PV cell, but in thin film application generally they won't use in many in the industry. They used in a transportation. That is, they use generally for the application of transportation, that is three-wheeler or two-wheeler. Generally they use for the this thin film. This one thin film PV cell. Okay, so totally three will be there: poly, mono, and thin film. So how can we select this poly or mono? Means, see, in polycrystalline, so we need to select if there is a higher sunlight, means like Rajasthan side, or in monocrystalline, even in a darker, in a lesser evening also, it will observe the sun power. But polycrystalline is not like that. Polycrystalline require the higher solar energy. So whenever the higher only, it will be running. But in monocrystalline, even in a normal condition, like evening condition, it will generally absorb the solar radiation. And there is a junction box is there. This junction box is nothing but what? This junction box generally connection purpose, like positive or negative, and back sheet will be there, right? Back sheet will be generally hold the all the material, and even the frame. The frame will generally hold the this glass and enclosement, solar cells, and everything. So next is how we define that solar panel efficiency. So to define the panel efficiency, we need to consider the cell efficiency and total panel efficiency. So in cell efficiency, if you take the cell efficiency, they have the cell design. Okay, if you take the cell efficiency, they have the cell design, and another thing, type of silicon material. So type of silicon material already told, whether it may be a poly or it may be a mono. So in panel, total panel efficiency, we need to know the cell layout. Cell layout means it may be a seriously mounted or parallelly mounted, and also panel size. So panel size means what is the size mainly, and what is the main effect on the panel efficiency, we need to know. So and also, so in order to know the panel efficiency, so to know the panel efficiency, the maximum power output divided by area into 1000 watts meters per square into 100. In generally in market, we are using the single mono PERC. So the single mono passivated emitter rare cell we are generally using. And in market, poly PERC will be available and mono PERC will be available. But the mono PERC has a higher efficiency compared to the poly PERC. Okay, so these are the things available in the market, but generally we use only two materials, that is poly PERC and mono PERC. But mono PERC has a higher efficiency, generally the poly PERC. So mono PERC is widely available even in market also, and also even poly PERC also available. So efficiency, percentage of panel efficiency is nothing but what? Is nothing but the maximum power output. Okay, maximum power output, single model I already told it's like 340 watt. So divided by what? Area into 1000 watt per meter square. So this is nothing but what? 1000. This is nothing but irradiation. Why? Because where irradiation will be generated more, then power will be generated more, means solar energy. If there is a less energy, less power generated, then there will be means less energy source, solar energy source, then will be a less power. So it is depend upon the solar power. So this is how we calculate the panel efficiency. The higher panel efficiency will be a single mono PERC, that is passive emitted and rail cell. Okay, when you know the comparison, actually I took data in the luminous India. So there are two types already told, poly and mono. So both are same, actually same means same with same 196, 99, 3.5 centimeter, both are same. In both are same, only the difference is 330 watt and this is 380 watt. Okay, this is also same 24 voltage and 24 voltage mono PERC and this is poly. So the main difference is only 50 watt. Okay, main difference is only 50 watt, but cost is also less compared to this one. So generally, depending upon the load side, we will use in domestic application. Generally, we use what? Generally, we use the mono only. Generally, we use the what? Poly. But in industrial side, in domestic application, we use poly. But industrial side, generally they use what? Mono, because they won't generally go for the money. But they actually go for the higher efficiency and also maintenance. So one generally coming days, what happen? Even the maintenance cost will be high, so that it will suppress the purchase cost. So in industry, generally what they will go for the higher solar panel only. This solar panel will coming year like that long term, like more than 10 years generally or 20 years generally they will install, because that much of warranty will be provided by the manufacturer. So generally they will go for the higher amount only, but they need a higher efficiency and also low maintaining cost in a coming days. So generally they go for the mono. But some domestic application we use the poly, which is less amount. So in domestic application, what generally they will use? Generally they will go only for the less money. But in industrial application, they go for the higher amount of money. Okay, but no, nothing change. All are, see, capacity will be 330 in the poly, and in mono capacity will be 380. And same open circuit also generally less difference will be there, and also maximum current will be same. So 8.68, 9.66, and same warranty period. See, performance will be 25 years. See, in a long term, generally they go for the mono. They won't, in industry, they won't generally go for the like price wise. Generally they go for the efficiency and the maintenance cost. Okay, and also we need to observe, means when we consider the poly or mono, but some wattage rating, polycrystalline model are large inside. In other words, monocrystalline models are space efficient. So generally in this they will go for the domestic or industrial application. And how to choose the PV model in residential and in commercial? For residential, for a large size space, generally we can use polycrystalline, and even for the small size, because small size, right, we need to extract more solar energy. And even in normal evening time, even the monocrystalline will help in the help in the generation generating the voltage, but not in poly. So in small size space, generally what we use the monocrystalline. Okay, generally what we use the monocrystalline. And for the commercial what? Commercial means already told for the industrial application. Commercial means industrial application also told they will use the monocrystalline, because I already told they will go for the efficiency, and even they will go for the mainly the maintenance cost. And even if we are in our home, if you want to design any solar panel, before that we need to know what is the roof size area, what is the availability. Okay, we need to know, and what is the pitch, means what is the angle of the roofs. Means some have some old soil type roof will be there, soil like Mangalore, and we will call in Karnataka. So generally we need to know the roof pitch, and any shading roof obstruction we need to know, and the direction of the facing. Some house will be facing in the south, or some will be north, and some will be directly facing to the east side, or some will be facing to the west side. So we need to know what is the spacing generally. So and also roof material, already told type of roof material, because when we installing the solar panel, there are different solar mounting will be there. So there another in at the end of the section, solar roof mounting will be there. But here roof mounting is important. So different roof mounting is there. Suppose even RCC roof mounting, we need to make the leveling, because the frame should be in a level. Okay, the frame should be in a level. So that is also important. And the electrical wiring and the climate condition and regulations. Climate condition generally, you know. So we have different season, summer and winter. Or some region will be there in a Western Ghats, complete there will be a no sunlight. Or some region will be there like near the North India. So almost like 8 to 9 months there will be a sunlight will be there. Not North means not Kashmir, like Delhi, near to Delhi, UP. So there will be more solar energy. But compared to the northern shore, we have the less. But we need to know the climate condition also, and also regulations also. So these are the things we need to consider when we installing the residential. So solar panel design. Okay. Now in a solar panel design, if you consider, we have the two systems will be there. One is on grid, one is off grid. So what is the meaning of this on grid and off grid? So in any PV system is connected to the grid. It is called what? Means in any PV system, means PV system is connected to the grid. So this grid will be there. This is called what? On grid PV system. There we have to synchronize the generator voltage with the supply voltage or grid voltage. Means in on-grid system, we need to synchronize the generator voltage with what? Supply or grid voltage. But in off-grid PV system, synchronization is not required. Means it is not required. So in that case, it is called what? In that case, it is called standalone PV system. Okay. And in off-grid system, you have two options. Two option means that it can be used as a AC load also, means left part will be off grid. It can be used as a AC load also, and also DC load. But where in on grid system, you have to go only for the what? You have to go only for the AC load system. So in off grid system, so this is the off grid system. See, the solar panel here is connected to the solar energy. And this PV panel converts what? Generally, this PV panel converts to solar energy into the what? Electrical energy. And it is given to the where? MPPT model, that is maximum power tracking module. So, and this maximum power tracking model, next it is connected to the battery and battery to the off grid. So, there are two different type of MPPT model. Generally, two different type is there. So, this MPPT model with two different, which I am telling, it is decade, means like more than 10 years they were using. One is structurally oriented MPPT model. So last session, LRSN sir told new MPPT model, which is good in research purpose. But this old structure oriented MPP model is what? So our generally what our sun will be there, right? The sunlight path may vary in a 2 times, yes, right? Because it will vary over a period of time. That is, in a 12 months, we have 2 seasons will be there. One is summer will be there, one is winter will be there, right? In every 6 months or every 5 months, it will be changing. The sun direction will what? Sun direction will be changing. So there will be a sun path change will be there. There is a sun path change will be there. So in order to observe the sun, observe the sunlight, maximum power, we need to give the structure oriented. Okay, we need to give the structure oriented. So another MPP model will be there, that is power translated boost converter will be there. So generally what that converts will extract the maximum power which is available in the panel. So each MPPT model will be discussed later. So after the MPPT model, the battery is going to store the energy. Okay, after MPPT model, the battery is going to store the energy. So whenever the solar power is available during the time, battery will be charged. At the same time, you can supply power to the load also. At the same time, you can supply the power to the load also. So here generally I have taken the load sides in like a domestic application like bulb or fan or refrigerator generally. So this is the on-grid system. Okay, this is the on-grid system. So as I told in off-grid system. As in this off-grid system, you have two options already told. One is DC microgrid and also standalone system. It is also DC means DC load can be given and also AC load can be given. So it is called. It has a two option, that is DC microgrid and also standalone system. So in standalone system, it is called what? AC system. So in DC microgrid also called as a called as a standalone system. Okay, also called as a standalone system. So actually near the future. So last session, so every spokesperson has spoke, and also in the first session they told about the current war. Okay, it's a very good information, and because in coming days, because in coming days what the domestic application load like a refrigerator, fan, mixer, everything will comes on the DC supply only. So in even some loads will work like a DC supply and also AC supply. So nowadays what both the AC supply and DC supply. So in that case, standalone system will be a perfect solution. And also whenever the solar power is option during that time, battery will supply the power. In case if you identify what is the backup time, because you need to identify, right, for that battery, for that supply, you need to identify the backup time and how many batteries are required and what range you have to calculate and everything you need to consider. So in this section, the main objective is to have the choose the standalone off-grid solar PV system to fulfill the domestic, like 1 kilowatt domestic application. So next thing is on-grid system. So on-grid system is similar to off-grid system, and the solar power will be transferred the same. The solar power will be transferred to the PV and PV to the MPPT model. So after MPPT, there will be a grid tie inverter model. So grid tie inverter model. So this will convert the sufficient amount or equivalent voltage. Okay, this grid tie inverter generally convert what? Sufficient or equivalent voltage. And the two things need to be synchronized here. So one is called voltage and another is called what? Phasor. Phasor is what? Generally a frequency. So here, this is also called what? Generally, so after this is a grid system. Suppose if you take the grid system is 50 Hz, because in a grid frequency is not constant matter. Okay, it always be vary based on what? Generation part or distribution part. And if there is a demand variation in the load also, due to the fact that grid frequency will not constant, due to the fact what? The grid frequency will be not constant. So in that case, we need to control the frequency with the help of what? With the help of this grid supply, with the help of this grid supply. So in this case, we have to take the grid frequency as a reference, and then based on this reference, we have to generate what? We have to generate PWM for the inverter model. Okay. So in this case, we have to take the grid supply frequency as a reference. Then based on this frequency, we need to generate what? PWM for this inverter model. Okay. So generally in on-grid system, okay, generally in the on-grid system, so we can call as a single model. Which one? This MPPT model and the grid tie inverter model. This is a single model. So in market, generally you can get a 1 kilowatt grid system or 5 kilowatt also. We can develop that 1 kilowatt and even 5 kilowatt also. So after this grid inverter, there is a bidirectional meter will be there. Bidirectional meter means this is nothing but what? Energy meter. Means it will generally monitor how much energy generated by the solar system. Solar PV system. Means how many energy generated by a solar PV system and how much energy is utilized to the distribution part. So generally it acts as an energy meter. Generally it will monitor the generation of solar PV system and also distribution part, and how much amount of energy is supplied to the grid, and even it monitor the how much amount of energy is supplied to the grid. So, and everything will be calculated using this bidirectional energy meter. So, in on-grid system, we have called what bidirection, because the grid to load and load to grid, it will be supplied. This bidirectional energy meter is also available in market. Also, this bidirection directly it will be available. So we can integrate and we can develop the normal PV system. So from this energy meter, the load will be connected via distribution valve. So from this energy meter, the load will be connected to distribution panel. Now the point is, you can supply the sufficient power to the system, and excess power can be transferred to the grid. So this is what the on-grid system. In on-grid system, the excess power what we can transfer to the grid also, and even we can give to the load also. This is what the bidirection means. Excess is given to the grid, and even through distribution panel we can given to the load. So in the absence of any solar power, you can take power from the grid. So another thing, yes, right. So even the whenever the power cutoff will be there, with the help of this bidirection one, so we can get generally power from the grid, ensure that any point the load will get the power, right? The load will get power. So this is the one of the advantage in the on-grid system. Okay. So what is the one major like different in on-grid and off-grid? In on-grid, in off-grid system, generally you will get battery. So, but in on-grid system, instead of battery, you will have a grid only. Okay. So this is the main we can measure like battery and grid. So the excessive power is fed to what in a grid system. In case we can earn money also. So okay. So now how to choose the solar panel generally means solar panel design. So in order to choose this solar panel design, there are the totally we have 6 steps we form. One is calculate the total load per usage time. Okay, we need to calculate the load and identify the sunlight time in your location. So that is our orientation angle. This is the important thing. And we need to calculate the PV panel efficiency. Okay, so we need to calculate the PV panel efficiency. Means if you follow this procedure, then you can build your own PV standalone system. Means you can decide the own standalone PV system, and all the components will be available in the market only. Means you need to identify for the particular model. Means suppose if you want to calculate the total load per usage time, so whether what is the average time. Okay, means average time means nothing but how much time it's gonna be working condition. Okay, how much gonna be it's a working condition, that we need to calculate the average time. And also identify the sun available time in your location or orientation angle. Means suppose you are in we are in Bangalore area, or even Chennai, or some people from Hyderabad or Delhi or Mumbai, they have identified the sunlight availability and orientation angle. We need to identify, right? Because the longitude will be different. Okay, the longitude and latitude will be different. Okay, we have one time zone, but the different longitude and longitude. So we will later we'll know what is the orientation angle in compared to Tamil Nadu or Bangalore, Mumbai. So we'll come to know next. And we need to calculate what? We need to calculate the PV efficiency. So what is the maximum of efficiency extracted, because the input solar light is not constant parameter, right? So it's not constant parameter, it's keep on varying. So we have to consider the panel efficiency. Yes, right. We have different season. We have to consider what? Panel efficiency. Then inverter efficiency. Since it is a electronic circuit, it won't be ideal efficiency. Means ideal means what? Generally a 100% efficiency. It's going to be what? Generally this inverter will what? Generally it convert to DC to AC. Generally it will be what? Some 25% or 20%. We have to choose in that one. Or even backup time calculation. This backup time calculation is the we need to know how much battery backup time. Okay, we need to know how much the battery backup time and how much it will facilitate to load. We need to know the backup time, and also cost analysis for the existing expense. Yes, right. So you can come to the conclusion that suppose if you are investing in PML module, how much time it will take to recover the amount. Okay, that is important. So that is the main advantage in renewable of PV. So if you are investing, we need to recover, right? So later onwards, we will come to know in calculation that some amount of money you can means when you are connected to the grid system, you can earn money. So another that one analysis of cost with what existing expense. Okay, the first thing, calculate the total load per usage step. Suppose I have taken a normal domestic application. Okay, normal domestic application. Suppose 60 watt bulb. Okay, 60 watt bulb. I'm taking 6. Okay, 6 per day, and the total watt consumption means 6 hours per day, and the total watt consumption will be what 360. Okay, 360 watt per day. And ceiling fan 150 watt, and the total usage is 8 hours, and the total watt consumption. Okay, this is 1200. Okay, okay, 120 are written. Okay, and 50 the total usage is 8, and it is 400. Okay, and 150 that is monitor I have taken. So 150 total usage per day is 3 hours. Okay, total is what 450 watts per day. Okay, so actually this is 1200. I made a 120. I made a mistake. So from this we have to calculate the number of units. Okay, from this what we have to calculate the number of units. So after that we need to apply the cost per unit. Okay, this is what the panel design will take, and finally we'll get a total amount we have to gonna spend within a PV expenditure. Okay, okay. I will share one Excel sheet. Okay, is it visible? Excel sheet.
Yes, sir.
Thank you, ma'am. Okay, suppose we have taken the bulb 60 watt. Okay, ceiling fan is 150 watt, and laptop is 50 watt, and monitor is 150 watt. So suppose we have taken the quantity three bulbs in a domestic application, and 4 fans, and 1 laptop, and we are charging, and another one is monitor 1. So usage per day 3 fan plus generally usage 4 hour will run, and what total watt required in a per day is 750 watt. So and ceiling fan, if you run 4 quantity in a 4 usage per day, that is 24,000 watt. And also laptop will be, suppose we have taken 4, that is 200, and monitor will be 300. So total daily usage will be what? Total daily usage will be what? 3,620 watt is the total daily usage. Okay. So in total daily usage, suppose we need to convert in a kilowatt hour, right? This is the watt hour, kilowatt hour. So 3,620 divided by what? 1000. Generally we get what? Generally we get 3.62 units. Okay, so this much of units we are generally consuming per day. So 3.62 watts. Okay, and monthly requirement. Okay, so 3.62 into what? 3.62 into 30. 30 will get what? 108 units. So this is the monthly requirement we need. Means before we need to design the solar, so we need to know the load requirement. Okay, so our load requirement for monthly, how much we are using? 108 units. And suppose this 1.5 rupees. So in Karnataka there is a different tariff, but for our calculation we have taken 1.5 rupees, and monthly cost will be what? Monthly cost will be 162 rupees. We can change. Suppose I will share the with the coordinator with this Excel sheet. Suppose if we change the generally the fan into the 4 hours into 8 hours. So it will change. Monthly cost will be changed. Or even if we change the usage per day, this is we design the this EP power calculation sheet. Okay, I will share at the end of the session. So we need to know. So monthly rate will be what? Monthly rate will be generally 160 rupees is our total cost, means usage cost. Okay. So next one is, so now what? Now generally we design. So now what? We design the total power calculation. So power calculation is what? Power calculation is we are using totally 3620 and a unit per day will be 362 and monthly will be 108 and this is the total money, that is 162 rupees. Okay. Okay. So now we need to know the panel design. Identify the step two is to identify the sun availability time in our location and orientation angle. Yes, right. So already told we have the
First
different.
slide was not.
1 minute, sir.
Checking, sir.
Sorry.
Previous slide, sir. 23.
Sir, I will share the slides at the end of the session and
Oh,
I
the
will
light
share
is
that
on.
calculation sheet also. Okay, sir. Is it visible, sir?
Is it visible now? Okay,
Thank you, sir.
Okay.
So I've taken rate per unit is 1.5. It's in Karnataka tariff will be different. Different state of a different tariff. Still electricity will not come under GST, but different yeah, electricity board has a different tariff will be there. But our assumption we have taken the 1.5 rupees. Okay. Next step is what? Next step is we need to identify the sun availability. So sun availability time in our location and orientation angle. Yes, right. So sun availability time and orientation angle will be different region for a different will be there. Example. So we have one thing, different location is different, and we need to know the summer and winter zone. Suppose the sun maximum energy during the summer, okay, and even the winter it will be changed, right? So the path will be changed, sun path will be changed. So we need to know the sun path. So in the sun path, generally what? Suppose the coordinates of Bangalore. Bangalore is what? 12.97 or Chennai is what? 30. So this is what the tilt angle we need to know. Okay, we need to know the coordinates, and with the coordinates we are know the orientation angle or what that is called tilt angle. So with tilt angle, generally what we mount the solar panel. So even in summer time or winter time, the movement of the sun will be varied. Okay, even like December, the month, the movement of the sun will be varied. Okay, and generally, if you mount the panel like east to west, generally what we mount the panel in a east to west path. And the sun path already told it is not in the same path. Each and every day, what a small degree of changes will come. Okay. Generally, while mounting, generally we take the constant of 12.7 like 13 degree. But each and every day, what a small degree of changes will happen. Means in winter, we have seen here drawing. In winter, there is some dash line will be there. It will not contact. It will move like summer. Means summer after summer, winter after summer will come. It will small variation of degree will be there. But generally in a thumb rule, what we need to mount the panel. Yes, right. We need to mount the panel that the optimal annual production of this solar panel of tilt will be should be equal to the geographical latitude. Means we are mounting in this geographical latitude. That is what 12.9 for the Bangalore. We need to know this latitude. Then we need to mount the panel tilt angle will should be 12.97. Okay, this will be different region. It will be this different. Means in this tilt angle, we can get the optimal
So
energy
sorry for
production.
disturbance, sir. The slide is not getting.
Sir, one, sorry, sir.
Actually, you're saying about the geometry, right? This one, sir. Right.
Is it visible, sir?
Now the slide is okay, sir.
Okay.
It is not on slideshow, sir.
Yes, sir. It is not a slideshow, but
First time I'm using, sir. 1 minute.
yes, sir. Now it is okay, sir.
Thank you, sir. Thank you, sir. I'm sorry for that, sir, actually.
Excuse me, Dilip.
Yes, sir.
Yeah, there is a problem in GeoMeet. Okay, so you
Okay, sir.
need to move slowly. Okay, whenever you are moving, no, slide by
Okay,
slide,
sir.
move slowly
Okay,
so
sir.
that it will be set right.
Okay, sir.
Now you can go ahead. Thank you.
Okay, sir.
You're muted, Dilip. Yeah.
Yes, sir. Yes, sir. So this is the what the orientational angle I was telling. So winter will be there, summer will be there. So it is not constant in winter means every winter it will be changing. Some odd degree will be changing. So we need to mount the panel of geography latitude. So in Bangalore told 13 degree and Chennai, if you search in a Google Bangalore coordinate, you will get the geographical latitude and longitude. Okay, so with this reference we need to mount the panel. So this is the general rule, right? The general rule for the optimal energy production is to set the solar panel equal to what? Geographical latitude. So this is what the orientation angle. So this, see the north and south. The south should be in a downward and north will be a upward. So this is what the tilt angle, and the sun we need to mount in a east to west. This one, sir. So this is in a roof side, means from the roof, and we are making upward, right? So upward will be north will be upward and the south will be a downward. From year to year, this is what the tilt angle. Okay, from year to what the tilt, or we can call the orientation angle. Suppose, okay, 1 minute. So this is the sun tracking MPPT using MATLAB. So actually this is the older method. This tracking generally we are using in a motor control. So what Elizabeth said, with the help of now machine learning and also with the help of generally IoT, we can control. But this design generally from used earlier in industrial technique, they were using in earlier, means last 2 decades they were using this motor control power tracking. So this tracking will be from morning 8 to or 5. This is how the motor, with the help of that motor, they will be tilted, the panel will be tilted so that the maximum power can be observed through sunlight. So this is the old MPPT. And in also market, they are the CPV solar structure. So concentrated PV solar structure. Concentrated means suppose we have the 5 kilowatt panel will be there, and this 5 kilowatt panel will be mounted, means single module panel will be there. But in suppose we are designing a 1 or 5 kilowatt, in a 5 kilowatt panel will be mounted in a single frame, and with that frame we are rotating. So this is also old model will be available in market. But generally in the new research is what new research is, with the help of machine learning or deep learning. So we are extracting more power, so using that MPPT. So this is the new research topic, that we are using machine learning and deep learning, and in algorithm we are using AI, PO. So that is in we are using in a MPPT. So this is another one new research option for the research scholars. So using this machine learning or deep learning, we can gain the maximum solar power and extract more power from the panel. So machine or deep learning. Suppose if you take the 600 watts panel, means here, so I already told for different temperature there will be different power will be there, means power what extraction power will be there. Suppose for 25 degree we need a, means our load is what, our load is generally 600 watt panel, we need a 600 watt panel, but what we are getting from the panel will be what, panel will be 426 watt, means we are a shortage of watt. So what we'll do, we will increase into what, we will increase the panel capacity. Okay, we increase the, see, earlier panel capacity is what, earlier panel capacity is 600. Now, but even that 600 panel capacity, we are only getting what? Only getting 426, means we 1 minute. See, we need what? We need generally, so not 1 minute. Okay. Okay, see, we need what? Daily usage is what? Daily usage is 3620. Is it the Excel sheet is visible? Okay.
No, sir, not visible, sir.
Okay, sir, 1 minute.
Yeah, now it is visible, sir.
Thank you, sir. Suppose our daily requirement is what? Daily requirement is 3620. Okay, our daily requirement is what? 3620. So in that 3620, the sunlight availability is only for the 6 hour. Maximum sunlight tracking will be only for 6 hours. Means if you divide the 3620 with the 6, how much panel requirement? Panel requirement means we need to design the panel is how much? The panel requirement is 600 watt. Yes, no, sir. So we need a 600 watt panel. But in our temperature, what we are in our temperature, but in our temperature, we are lagging. We are lagging of nearly 180 wattage. So what we done, we increase the panel capacity. Earlier our panel capacity is only 600 watt. Now we increase the panel capacity to 1 kilowatt panel. Why? Because we need our load condition, what our load for every day will be, we need to get 600, right? But earlier in a 600 watt panel we are lagging 1 to 180. Now with the 1 kilowatt panel we can generate 630, means with the help of 1 kilowatt watt generally we can design the panel. Suppose see, earlier already told, earlier what we took, it is a lagging of what, 480. So generally how much panel requirement? Panel requirement is 600 watt. So in a 600 watt, how much module we need? The module we should be generate of 1 kilowatt we need it. Okay, this is how we need to design. And next thing is inverter efficiency. So we have the inverter efficiency. Already inverter will be not in a ideal. Suppose if you take the inverter efficiency like 70%, so the total watts will be how much? The total watts requirement is 3620. So the efficiency, if you consider the from inverter is 0.7, and the watts will be generally the inverter efficiency what? That is 5001. Generally we need the volt ampere. So that is what 5.1 kilovolt ampere. Generally we need a inverter efficiency. Okay. So, and also battery backup time calculation. So battery backup time calculation means, so we need a battery ampere. Suppose this one, what 12 volt ampere is there, right? So 12 volt ampere is not a inverter voltage. It is a battery ampere, and sorry, this is the battery ampere 150 ampere and 12 volt voltage, and number of batteries will be 2, and the efficiency of the battery generally we are no, not efficiency. Efficiency will depend on the battery rating. Okay, and we have taken the power consumption. Suppose the inverter efficiency is what? Inverter efficiency is 70%. So the volt ampere for the selection of the inverter is what? 5.171 kilovolt ampere. That is what? 5.1 kilovolt ampere. And the panel rating, already told, panel rating will be 24 voltage. And the system voltage is what? System voltage is 12. And battery rating will be 12 ampere if you take, 12 volt and 100 amps. And number of batteries will be 2. Okay, number of batteries will be 2. And suppose if you take the battery efficiency 80%, or even we need to know the backup time. If the battery is only 2 will be there, then our backup time is only 31 minutes. So if we increase the battery capacity of 4, so we can increase battery backup capacity will be 63. So depending upon the inverter efficiency and the battery rating, we can came to know the how much backup time of the panel design. Okay, next thing is, so this is the total off-grid PV system. So from sunlight to solar panel. In solar panel, what we have taken the 600 watt because our load calculation is 603, our daily requirement. So we design the panel of 600. So in
Sir, sorry for
600 watt.
interrupting you, sir. Sir,
Sir.
you said that inverter efficiency 70%. Na? Whether either the efficiency has to assume whatever will be the efficiency is
No, we assume the
or else
efficiency,
you have
sir,
to take
for
70%.
we assume the efficiency. Efficiency will be 80. For our calculation, we done a 70. That how much we need a backup time. We assume that much, sir. Because
Okay. Suppose if we assume that inverter efficiency 90%, is it okay, sir?
sir.
Suppose if I want to assume that inverter efficiency as 90% and battery efficiency is also 90%, is it okay for designing?
No, sir, it depending upon the inverter you design, because inverter part generally, yes, we only what from battery we are supplying to the AC loads. So
Okay.
depending upon what type of battery, and there we are calculate the backup time, sir. Assumption is for only for the calculation, not for the designing purpose. For designing purpose, if the battery backup time, then okay, but in general, for the research purpose, we cannot assume, because inverter efficiency will be vary, but it won't be idle. That one for calculation requirement I took for, because I need to know the backup time and efficient. For that backup time, I've taken the inverter efficiency. Inverter efficiency on manufacture it will be varied, or if you design in a research purpose, you will get the maximum inverter efficiency, because research we need to go for the maximum.
Maximum, yes, sir. Right.
Yes, sir. Only for designing backup time I took. Okay, if the inverter is efficiency is, because this is the market thing, I have taken the efficiency and battery, but it's not a ideal means 100% or just for the calculation of backup time. Suppose I told no, sir, it will vary because suppose if you design the inverter and inverter efficiency is you will get near to the year, then you can change how much backup time you can design the battery, right? So that calculation I took, sir. That's it.
Okay.
Okay, thank you.
Thank you, sir. Thank you.
Okay. So for 600 panel, so this is 600 watt. We took 300 watt panel. Sorry, this is not 3 panel because we had took 1000, right? Because 1003 panel we took, because from the 1000 kilowatt we are getting what? We are getting 600 watt. So that one EB calculation Excel sheet we got what? Generally 610. So after that, what? This is the one model. One model, the inverter is what? 5.17 kilowatt inverter model. And this one I already told, right? For if there is a battery will be like 4 will be there or 2 will be there for 48 minutes. Means we are designing, depending on taking the inverter efficiency, we are designing the battery. Okay. From there to inverter, we are giving to the loads. So I have taken the loads that one number of laptop or bulb or monitor or the domestic application. This is what we design. And generally, this complete for a setup for the 1 kilowatt power system, I took it my friend only. So these are the things we required for the complete setup. Okay. So this cost nearly 70,000. This place is not included GST. 70 plus GST, sir. It's included like another, like you have transportation cost, another thing. But in order to design the 1 kilowatt in domestic application, at least we need some 70, 75. So I took it from the quotation from my friend. So complete setup for the 1 kilowatt power system. And suppose here, so our daily calculation is what? 3,620. Okay. Our daily calculation is 3,620, and the daily units will be divided by 1000. It will be 3.6 units. And suppose the monthly requirement means 3.62 into what? 3.62 into 30 means what? 108 units will come. So in 108 units, generally some states, suppose example like Tamil Nadu or Karnataka or Andhra, some states will calculate tariff on bi-monthly. Some states will calculate monthly. So in Karnataka it's difficult because we have subsidy, and some states they calculate in bi-monthly. So I took both in monthly requirement and bi-monthly requirement. Suppose the rate will be like 3 rupees. So that monthly cost will be what? 180 into 3, we'll get 325 rupees. And bi-monthly, it will be 651. So PV generation per day is what? PV generation per day units will be what? 3.83. And for monthly generation will be what? Bi-monthly, it will be 230 units. Means we are saving, because in monthly requirement, what bi-monthly generally, so we are getting 270, but in solar we are generating more than that unit. So remaining 12 units will be what? Remaining 12 units will be excess. We can we earn money from this, and we can generally meter will be there, right? So we can earn money with the help of this solar design. Means 1 kilowatt, depending upon the load, if we design, if the excess will come, we can earn money. Okay. So this is the normal PV cell modeling, a simple PV cell modeling design. So this is the cell, and this is the irradiation. Okay, irradiation means solar radiation. With that, we have given the variable resistance. Okay, with that we have given what? We are given to the variable resistance, and we can see here current and voltage curve. This is the current and voltage curve. Here, if the current will be raised, then the voltage what? At some point, the reference voltage will get what? 0. So we need to take this point so that the maximum current and maximum voltage we should get. Okay, generally. And also in PV curve, so if we calculate IV, we get power and voltage, and this is the maximum point which we can get the power. So generally what? Generally,
Excuse me, sir. Are you showing our The same slide is on the screen. Are you showing or explaining only, sir?
No, ma'am, I'm sharing, ma'am, actually.
Thank you, sir.
Dilip, your voice is not audible. Kindly check. Please.
Sir, is it full screen mode, sir?
No, it's not in full screen mode. Yes. Still it is not.
Sir, now?
No, still it is not in full screen mode. Yeah, correct. Infinity. Dilip, are you there? Dilip, you can try from the slideshow on top. Home, insert, design, transitions, animations, slideshow. Yeah, you can try from that. Maybe from beginning or something, wherever. Yes. From current slide. If it doesn't come, it's okay. You please proceed.
It is also visible, sir, no problem.
Yeah, Dilip, you can please proceed. No issues. Dilip, are you there?
Sir, is it full screen visible?
No, it's not visible, but still it's okay. You can continue, no issues. Okay, later we can.
Sir, it is visible.
So you
Okay,
can
sir.
continue, sir, with this
Sir, it
also.
is visible. You can continue.
Okay, thank you, sir. Okay, totally there are three type of roof mounting structure will be there. So one is solar panel mounting structure will be there, rooftop, tin shed, and ground mounted. So rooftop means generally what in a floor roof will be there, rooftop. Generally before mounting we need to know the leveling. We should do the leveling. Some of the civil work we should do. Then we should start the mounting. Without a proper civil work or a proper flat, we cannot do the mounting because some panels will tilt in a upside in a east side, or some panel will tilt in the upside in the west side, so that the maximum tracking won't happen. So we should careful while doing the rooftop mounting because we should do the leveling. So next one is tin shed. Tin shed generally we have seen, right, whenever the shed will be there, shed type structure houses will be there. There we will make the frame, then we will mount the solar panels. Then last one is what, ground mounted. Generally the main solar park which we see, those are what, generally those are ground mounted structure. So what we told Rajasthan, in ground mounted structure also we need to know, we need to make the exact civil work so that there will be proper plane should be there. If there is no proper plane, then the tracking of solar position will be reduced. Then panel efficient means panel solar absorbing power will be reduced. So both in rooftop or both in ground mounted or even tin shed, the leveling is important. Without proper leveling, then the mounting structure will be difficult. So next thing is, we already told MPPT culture. So MPPT, what generally MPPT generally have the main thing. So last session they told about many things about MPPT controller. So main function we here what we get, it will take a wake up call. Wake up call means generally in this control generally from PV source. So from PV source, how much maximum power track can be achieved through this solar panel? It will be with the help of what? With the help of what? MPPT control. So MPPT control is what? It is a some type of what? Algorithm. So it has a charge control for what? Generally for extracting what? Extracting maximum available power. So in PV model. So certain condition, what you know, the certain condition when there will be ambient temperature will be there, or sun solar cell temperature or solar radiation means sometime it will be a cloudy. So depending upon that, but still MPPT will be have algorithm so that to extract the maximum solar power. And last thing of this session will be earthing. So we have the two types of earthing generally for designing the solar panel. One is AC earthing, another one is DC earthing. So what is earthing? See, from sun to the solar panel, we have the DC power only. So there what we'll do, so there we will do the what? DC earthing. So after means suppose in earthing we need to consider there will be indoor will be there, outdoor will be there. Outdoor will be what? Outdoor will be sun and panel will be there. Indoor what? Indoor generally MPPT model will be there, grid inverter will be there, and load will be there. There we need to do the earthing, because why? Because generally when we panel and generally it will be there, lightning will be there during rainy season, it is difficult, right? Light, whenever the lightning strike, we need to do proper earthing. So that is the important. So that for that we have the two types will be there. One is AC and one is DC earthing. So until you know from panel what generally we get DC means the battery pack. Okay, battery pack, even standalone inverter. General, see there are three earthing will be there. So one is for charge control, we have the different earthing means panel, from panel to charge control we have the different earthing, and from battery to AC circuit means generator backup, they have the generator, they have the different earthing. We need to do for the generator backup different earthing. And from panel charger control, we need to do the different earthing. So for DC circuit to AC, this one, DC circuit and DC connected, and AC power and standalone inverter, we need to do the AC earthing. So this is what I told, different AC earthing and also DC earthing will be there. Suppose we are designing the 1 kilowatt panel design. For a 1 kilowatt panel design, we don't need any earthing, because whenever we go the higher kilowatt, like 5 or more than 5, we need a panel earthing. And also this is some example of earthing. Say enclosed earthing will be there, some example. Okay, then this is the panel and this is the structure earthing will be there. These are the some of the example. So we need to consider, suppose in cities, okay, in cities, suppose in your home in a flats, it will be like 8 floor, 10 floor, tallest building in our area, then definitely if the 5 kilowatt is there, definitely we need to go the earthing only. Okay, because if the city your building will be the lower, then you don't need below 1 kilowatt, you don't need any earthing. That is also important. And even we have the lightning arrestor. In order to protect the lightning, even we need to do the earth for the lightning electrode. So already told, one is for inverter AC, we need to do earthing, and also PV model which is DC, we need to do the earthing. So we need earthing compound already told. So generally in market only available earthing, different type of earthing will be there. For normal kilowatt, already told, like normal kilowatt, 5 kilowatt or like that, generally you can dig up for the 3 to 5 feet is okay. But more than like 10 or 20 kilowatt, you have to dig up like minimum 8 feet. So minimum 8 feet only we can do the earthing kit. You know how the earthing will generally do. We do the generally mixture of salt, charcoal, and sand. So generally we do the earthing. So these are the market solar available in India. Generally Vikram, Vare, or Gold, Tata Solar. Generally Tata Solar in electronic city only. Sun Loom. These are the top 16 manufacturer of solar panels in India. So this is about the solar panel design. So I'm sorry for my slides which are not invisible. I am not used in this GeoMeet. I'm sorry for this. Okay.
Yeah, Dilip, it's okay. Actually, yet to you will share the PPTs, so
Okay, sir.
participants can come to an understanding. And Hannah, madam, are you here?
Yes, sir.
Yes, madam. Dear participants, let's go ahead with the photo session. So, all of you, please open your cameras. Dilip, you also please open your camera so that we can take a photo. Okay. We have around 120 participants today, so please be patient. Okay, I will take nice photographs.
ಐದು ನಾಲ್ಕು 900 ರೂಪಾಯಿ ಕೊಟ್ಟಿನ ಅದ್ರಲ್ಲಿ
Dear participants, thank you so much. And Dilip, you have given a great insights of solar panel design. So now the platform is open for all participants to go ahead with the questionnaire. So if you have any more questions, you can ask Dilip sir so that he can answer your queries. Yes, any more questions are there? Anything in chat window? Nothing. Thank you, Sri Shaina. Thank you so much. Very good.
Sir, good evening, sir. In that slide, you said that the tilting angle, na?
Yes, sir.
Is the tilting angle has to change any within a specific duration or based on the season, sir?
No. Presently, for normally earlier mounting, it will be fixed. Okay, and they were
Okay,
using
sir.
for the earlier when they started panel, then they implemented in a motor control. Now they have the machine learning, so machine learning will track automatically. So only the tilting angle will be fixed for the specific latitude. Then it will tilt. Okay, yes, fixed that one.
Actually, you said in that slide in the winter season and the summer season, we're having two different seasons now.
Yes,
So in
sir.
that winter season, we are having one certain tilt angle.
Yes, sir.
But whereas coming to the summer season, the tilt angle must be vary.
That tilt angle will be vary.
The tilt angle has to vary, or whether it is a fixed one, sir. When comparing with
In
both seasons.
sir, both season will be generally same because the
Okay.
latitude longitude won't change, but the sun direction will be changed. But we have the now we have the deep learning. The maximum tracking will be done by the deep learning only, but tilt angle will be fixed, sir. That one even in the both because
Okay. Okay, sir. Thank you. Thank you. Sir.
okay. Thank you, sir.
Yeah, myself, Dr. Manjunath from Davangere.
Sir.
Is it audible, sir?
Yes, sir. Audible.
Yes, sir. Myself, Dr. Manjunath from EEE Davangere. See,
Yes, sir.
in our presentation, you have discussed the different design platform of solar panels.
Yes, sir.
Okay, that change in the design will make any changes in power electronics devices which we are using for conversion in PV power plants?
So change in design, didn't understand. Change in design in?
Okay, you discussed regarding 2 to 3 design parameters of solar power plants, solar panels. Okay,
The
change
solar
in that
panels,
one
thin
will,
film, mono and poly, sir. You are talking about that one.
that installation we discussed the different design techniques, installation techniques.
Okay, okay,
Okay,
sir.
that installation
Rooftop,
technique, that installation techniques will make any changes in power electronics converters.
power electronic means desired installation means suppose you are telling that like every criteria like rooftop or
No, yes, yes.
orientation that will be affect in that it will affect on the inverter design you are asking.
Oh, yes, sir.
Sir, that one I didn't consider that one. I didn't develop. One thing you just take my number, sir. I have some industrial like some contacts will be there in Tata Solar and even maintenance and even in installation. I will give their number. You can visit their plant and you can get to know that one. I can do that one in real time for that.
Okay, sir. Okay. Definitely, you just share your number, sir. I will contact.
Okay, sir. I will have some industrial person in manufacture or even installation. I will share their number. You can contact that one.
Okay, sir. Okay. Thank you.
Thank you, sir. Okay.
Sir, good evening, sir.
Sir, good evening. Tell me, sir.
Any new technique is adapted for the solar panel cleaning right now, sir?
Sir? Hello, sir?
Any new cleaning?
Sir, your voice is breaking.
Yeah, sir, you can speak, sir.
Is there any new techniques are adapted for the solar panel cleaning, sir? New techniques.
New techniques in solar panel adoption, sir.
Cleaning of the solar panel.
Sir,
Yes, sir.
new technique in solar panel adoption. Sir, generally
Yes, sir.
solar panel
New
adoption, the new techniques are leaf techniques is coming, floating will be there. Leaf technique you have no. Generally, the earlier they have what earlier they have like mounting will be there. Now the leaf technique will be came. Leaf design technique in like leaves will be there, sir. Like normal plant leaf, they are designing in a like that, and even a floating technique will be. They were bringing new thing. So these are the new research topics also happening in the leaf and floating. These are the new techniques they were presently in the market, not in market, in a research.
Any cleaning techniques, sir? Cleaning of the solar panel.
Sir, your voice is disturbed, sir. Durga, sir.
Shyam, sir, you can type in the chat window so that we can communicate to Dilip, sir. Dilip, there are some questions from the chat window.
Okay, sir.
If you want, I can read it actually.
Oh, okay, I will read, sir.
Yeah, Punita madam is asking. Is there any industrial visit or internship for solar manufacturing side?
Solar manufacturing. Yes, ma'am, I can get that one, solar manufacturing.
Punita madam.
Even okay, sir. Should I inform that one, sir? Is it in Bosch, where I am working Bosch, presently they were organizing the industrial visit for the 5 days. If anyone interested, they can contact me. You can take number from Dr. Kishore Kumar, sir. So, and also some of other industry, they were organizing the industrial visit. So I'm getting that one also, some information. I will share with you that also.
Yeah, there is a question.
Solar cleaning, yes, sir. Solar cleaning method still they were actually earlier they have the fixed timer for watering the solar, yes, sir. Panel cleaning. Now the new design technique they were in a panel designing only they were bringing, so that even because normally generally the water suppose in like in a desert area, if they're using, we are difficult to take the cleaning in there the desert or even some of the remote location. So in panel designing only they were bringing a new technologies, so that anti-dust or anti-material they were bringing, sir. In glass material will be there, sir. In that glass material only they were uh, designing, so that the anti-dust it won't affect the maximum power tracking. That the new method they were bringing, sir. Because earlier we know they were using the generally sprinkler method only, but it needs a lot of water, or even in remote location it is difficult.
Sir Dilip sir.
Yes, sir. Good evening, sir.
Sir, actually I have one question.
Okay, sir.
Minimum of 1 kilowatt installation, how much cost is needed in Karnataka region side, sir?
Sir, Karnataka region, my friend only, he was a vendor. He gave the quotation of 70 plus. I can share his number, sir. You can talk that one. The whole material, he was in a solar installation, one in Bangalore region only. So I can share his number. Even some other are there, 3, 4. You can get quotation. You can talk with them, sir. Actually.
That is the minimum cost we need to for 1 kilowatt.
Yes, sir, 1 kilowatt, because materials we need and the panel only it will cost more, sir, for 1 kilowatt panel only, and remaining thing it won't cost much. Yes, sir. Because panel and also a frame, you know, the aluminum frame, and aluminum frame will cost more compared to the normal iron. But iron, it won't be rust will be you will get rust, but you have to go for the aluminum, and wiring will be less, and battery system you need another cost. Battery and panel will be higher cost. So he gave the quotation nearly 70 plus, sir, actually. That is not included GST.
Sir, our existing inverter we can accommodate solar panel, no? As we using charge controller and MPPT, we can
Yes, sir. In existing only. Okay, sir. That one it will be possible, sir.
That cost again reduces because battery and inverter is there, means only solar panel will be the costing.
But it will affect your efficiency, na, sir. If the panel, because panel is observing the more power and your controller as a efficiency is less, that will affect your output power. But you have to change in a new methodology only. They will design in the inverter efficiency. If the panel efficiency is more, suppose if the panel receiving power will be more and inverter efficiency is less, you won't get the output more power, sir. You need to vary that.
It will not supply more.
So they have the different panel audit or mono. They have the perk will be there. The different panel will be there, sir.
Yes, sir. Okay, sir. Okay, sir. Thank you, sir.
Okay, sir.
Dear participants, actually Dilip is my PhD scholar and he has the ample experience of teaching so many industries. So being a teacher, he has a great exposure of industrial knowledge also, because he is seeing all the industries. He is collaborating with the industrial persons there. So we feel that we can get a lot of contacts from Dilip. So we can make use of his services for sure. And I have already shared all the phone numbers and all the email IDs of all the resource persons. In that, Dilip is one among them. So you can make use of his services also. He is a very good person and helping nature person. So wherever the things are there, he can open up. Frankly speaking, many industries are open the doors for academia all these days, maybe for students or for faculty, maybe for some days of internship. Even for faculty also, some days of internship they are offering. But the problem is we are unable to connect with them, and once they are disclosing, we are unable to see and unable to grab the things. So this is what exactly happening. In the gap between industry and the academia is still there. So we try to cover it up so that engineering will be much more fruitful to the all engineering students, budding engineers. Okay. So if you have still more questions, you can please ask, and maybe within 5 minutes we can close this session, because the next speaker is ready to give the presentation. So who is this? Maybe Mana sir. Are you speaking, sir? Mana sir? May I know who is this? If you want to speak, you can speak. Yeah, Hannah madam, you please give the vote of thanks to Dilip sir, and we can take it further.
Yeah, thank you, sir, for the practical session about the solar panel design and its implementation. Thank you for answering all the questions. So now we are moving on to the second session of this evening. I would like to introduce the second session of this day speaker, who is going to deliver his speech on intelligent microgrid operation and control by Dr. Chandrasekhar Permula. I would like to give a brief introduction about the speaker of this evening. Dr. Chandrasekhar Permula received his PhD degree in electrical engineering in the area of renewable energy based smart grids from Indian Institute of Technology, Delhi, and is currently with the School of Electrical Science, IIT Bhubaneswar. Dr. Chandrasekhar has received Young Scientist Award by National Environmental Science Academy in the year 2020, Early Career Research Award from DST Government of India in 2016, Young Engineer Award from Institution of Engineers for the year 2017, prestigious Indo-US Postdoctoral Fellowship to conduct research at University of Illinois in the year 2017, served overseas postdoctoral fellowship to do research at Aalborg University, Denmark in 2017. He has been selected as transnational access researcher as well as to work at the National Smart Grid Laboratory, Norway, under H2020 program. He is a senior member of IEEE and he has received the Innovative PhD Thesis Award, Best Thesis from the Indian National Academy of Engineering for the year 2015. Dr. Chandrasekhar has received International Travel Support Award as a young scientist from SERB DST Government of India in the year 2016. He has been awarded with Madhusudan Memorial Gold Medal by the Institution of Engineers in 2009. He won the title Best Innovative Idea from the Energy Resource Institute, University, Delhi in the year 2011. He has been selected for the student support programs of IEEE Power and Energy Society in the year 2012 and IEEE Control System Society in the year 2013. Sir, we are honored to have you in our midst. The session is over to you. We are waiting for the knowledge that to be shared on this evening. Thank you, sir. Over to you, sir. Chandrasekhar, sir.
Chandrasekhar, sir.
Thank you very much. Thank you for inviting me to deliver the talk in this workshop. In fact, I'm happy to see more than 100 plus participants are there at this time, and people are eagerly and enthusiastically interacting with the speakers. Very happy to, it's a happy note as a speaker as well as a learner. Yeah, so that is the best thing or the positive thing once I joined this meeting. Hi, sir.
Hello, sir. Namaste, sir.
Yeah. Thank you. Thank you again. So as we're all close to 8 o'clock, and the talk as per the time, it may take beyond 9 o'clock. So let us, without spending much time on this, let's directly go to the today's discussion. So before going into the details, please everybody, one small request from my side is that please feel free to interrupt me, probably if it is okay with the organizers. Is it okay, sir?
Yes, sir. Yes, sir. Please.
Yeah. So because many times these online sessions, it's something like that one-way traffic, and we'll not be having any discussions. So, but let us make it more interactive, and let us have it more kind of a live session. So we will just try to make it in-person talks, in-person discussions as much as possible. So that's my request to all the participants. Just interact, and please don't mind to interrupt me during the talk or during the discussion. Okay. So thank you. So yeah, I'm just to have avoid the bandwidth issues, I'm just turning off my camera and I'm sharing my screen. Yeah, please confirm whether my screen is visible or not.
Not yet, sir.
Yeah, I'm just doing it. Yes, is that visible?
Yes, sir.
Yes, sir. Now it's visual.
Yeah, so my slides, I think slides are visible, right? Slides are visible?
Yes, sir.
Yeah, fine. So welcome to the talk. So intelligent microgrid, specifically operation and control. So we'll discuss something of microgrid. So before going into the details of the microgrid, let us just try to understand why this microgrid is important. Or I'll just brief you what people are talking about the smart grid. Probably I believe that some sessions also might be there in this workshop on the smart grid. So I'll just give you a brief of a smart grid. Thereafter, the significance of the microgrid, and what is the necessity to have intelligent microgrid. Why a passive microgrid is not good enough, or why it is not sufficient to meet the requirements or aspirations or objectives of today's power and energy sector. We'll just have a discussion on it, and thereafter, what are the different types of operational modes of the microgrid, and what we need to do to control this microgrid to achieve the desired operation, and ultimately the different objectives of the intelligent microgrid. Hope that is clear. Is it clear to everybody? Yeah, I told you, please respond.
Yes, sir.
Yeah, okay, thank you. So before just going into the details, let us just try to understand what is our electric power system. What is our electric power system, and what we have studied so far. As you can see it here, the electric power system, it is as you can see it here, the electric power system consists of units for electricity production, devices that makes use of the electricity, and the power grid that connects them. So what do you mean by the units for electricity production? What do you mean by this? What are the units that produces the electricity? What I mean, what is your understanding of this?
Power generation.
Generators, very good. So we're talking about the generators. So power system consists of generators. Thereafter, the devices that makes use of the generated electricity. What do you mean by this? Loads,
Loads.
very good. So we are talking about the loads that makes use of the generated electricity. And finally, the power grid that connects these generators and the loads. So we are talking about our transmission and distribution system. So electric power system consists of generators, the loads, and the network that connects these two. That's what our electric power system. So when you are having this power system, what is the ultimate objective of this power system? This power grid, to be more specific. So the aim of the power grid is, as you can see it here, the aim of the power grid is to enable the transport of electrical energy from the production to the consumption. So we have to transport the generated electricity from the production, that is from the generation point to the consumption, to the devices, basically to the loads. And it has to achieve this objective while maintaining acceptable reliability. Acceptable reliability. See, to be more practical, so 100% reliability we cannot achieve. As a consumer, we expect or we prefer higher and higher reliability. Whereas if we make the higher reliability as a constraint or higher reliability as necessity requirement, in such case, considering the practical aspects, it may not be achieved 100%. Definitely, it is not possible to achieve the 100% reliability. But how near to, means what near to 100%? That's what we have to see that. And this number, the reliability level, what we are talking about, that should be acceptable to both generating station as well as to the consumers. So for the producers as well as the consumers. So acceptable reliability are to be more generic to all the stakeholders that are involved in this process. Acceptable reliability and acceptable voltage quality. So when you are saying that voltage quality, what do you mean by that? Voltage quality? Yes. What do you mean by voltage quality? Yeah. So we should not be having any sags. We should not be having any cells, right? It should be having a desired frequency, and it should not be having any distortions. So altogether, we should not be having any flickers. So whatever the power that what we are feeding, it should be free from all these distortions. It should be free from all these abnormalities. It should be free from all these anomalies. So it should be acceptable. It should be having the acceptable reliability, acceptable voltage quality for all customers, that is producers and consumers, are to be more generic, all stakeholders. And all these things have to happen at the lowest possible price. That is most important thing, right? So this is what our power system is, and the objective of the power system is this. Am I clear? Yes.
Yes, sir.
Yeah, please. So what do you mean by, now we are talking about, this is what our electric grid is. Now what do you mean by smart grid? Smart grid, if you see, a smart grid is an electricity network. As we have discussed, we'll be having generation, transmission, as well as the distribution. So smart grid is an electricity network that can monitor the electricity flowing within itself. So we should be able to monitor. The smart grid is the one which is having the information of what is that is happening within itself. So it should be that can monitor the electricity flowing within itself, and based on this self-awareness. So what it is going to do it with this information, what it is going to do with this awareness. So based on this self-awareness, it should be able to adjust to the changing operating conditions. All right. So we should be having the generators, we should be having the loads, and we should be having a network that connects these generators and the loads. That was our conventional grid. When it comes to the smart grid is the one having all these stakeholders, all these constituents. In addition to that, the smart grid should know what is that is happening within itself. It should be having the information of the voltage. It should be having the current that is flowing. It should be having the phase angles. It should be knowing the phase differences, the power factors, frequency at different nodes, at different points, or of different units. So you should be having all this information, and with this information, the smart grid is able to adjust to the changing operating conditions. Changing operating condition in the sense, please understand, the load is changing. It keeps on changing. When the load is changing, we should be able to adjust the generation. Or nowadays we're talking about the renewable energy sources. The renewable energy sources are time varying sources. So when mostly the wind and PV, what I'm referring to. So when these kind of time varying resources are there, we should be able to adjust the other part of the system. Let us say we may be adjusting the other generators so that the variations in the renewable energy sources can be complemented, or we may be going for the adjustment in the loads itself. That's what we call it as demand side management. So smart grid is able to do it with this self-awareness. Smart grid is able to adopt its parameters based on the self-awareness as per the changing operating conditions. And it has to happen automatically. As we can see that it has to happen automatically. And it can go up to the reconfiguration of the network, automatically reconfigure the network, and are exerting a level of control over the connected demand. That's what I said, the demand side management or demand response control. And the generation means the smart grid need to adjust its generation, it may need to adjust its loads, or it may need to adjust its network. Let us say we are reconfiguring the electrical network. We may be adding few more lines to the system, or we are turning on some of the existing lines, or we may be turning off some of the lines, the transmission lines or the distribution lines. So it has to happen automatically. The ultimate objective is achieving the system stability, reliability, the voltage quality, and at the minimum possible cost. And always these objectives will be having the different priorities based on what condition we are in. All right. So that is what the smart grid is. Traditional grids, we know that the power has been generated by the small number of large power stations. So the number of generator stations are small, but their capacities are large. So this transported electricity, we use it to transmit over high voltages to the means at high voltages over the transmission lines to the loads. At the load point or at the distribution point, we are going to step it down and we are going to supply it through distribution network to the loads. And in this case, the power flows are unidirectional. The important thing is that unidirectional. So what do you mean by unidirectional power flow? Can anybody say? In traditional grids, we are saying that the power flows are unidirectional. Yes?
From source to load.
From the source to load. Madam, power can only flow from source to load. Only the real power. Okay. Of course, the reactive power, we may be having a different arrangements, because as such, we will not be having any kind of, what we can say that the source or load. If we just go into the details of the reactive power, that is difficult to define because it keeps on changing its nature. In any way, in any case, we'll be having the power flows that are happening from the source to load only. So what do you mean? What is the so speciality of mentioning that the power in a traditional grid flows, or power flows in a traditional grids are unidirectional? It is something like this, madam. As you can see that everybody, as we said here, we are going to step up the voltage at the generating station, and we are going to step down the voltage at the distribution station or at the loads. So always we will be having the power that are flowing from high voltage end to the low voltage end. As such, we do not have the power flows, or will not be having any power flows from the low voltage end to the high voltage end. That is what it is happening in our traditional grids, right? However, when it comes to the smart grid, it is not the same. Before just going into the details of the smart grid, so what we have done so far, it is something like that. We have built a generating station, or we were having the loads. Let us say we are having the city. Maybe most of you might be from Bangalore city. So we are having the city and they are having a different loads. Okay, let it be. Okay, so we are having the loads, and to meet this load requirement, we are building a generating station that is somewhere away from the loads, and we are going to connect this generating station with the loads. And we are going to step up, and here we are going to step down the voltage. Always we will be having the power flows from high voltage end to the low voltage end. So we have built the generating stations, and we have connected these generating stations with the loads. So we just followed the concept of build and connect. Now, distribution networks can no longer be left to their own devices. So far, we are not touching the loads. So far, whatever the load that is required, the load is demanding, we are trying to supply the load that is demanded by the section of the loads, or the part of the loads, or the group of the loads. However, we cannot leave them for their own decision making. We have to have a coordinated decision, and that decisions have to be taken intelligently in case of smart grid. So I'm referring to the demand side management. Please understand this. Instead, they need to be actively managed. They need to be actively managed to cope with the rapidly changing the demands on the network along with the consumers they serve. So we have to manage different loads actively based on the operating conditions. Operating conditions means, please understand, it is not only the load but the generator. Not only the generator and the load, but the network. What kind of network? What is the network? So based on this, we should be able to adopt our system, and we should be able to take the decisions, and we should be able to meet the changing operating conditions stably and reliably. Okay, so a new network can be, so to meet all these requirements, we are saying that we have to change the generation. We are saying that we have to control the loads. We are saying that we should be able to switch on or switch off the transmission or distribution networks whenever we want. So all these things, if you see, we need to have a lot of monitoring. We need to have a lot of controls. We need to have a lot of protection equipment. So all these things, if you see, to meet all these things, we need to have a lot of digital controls. So to meet all these objectives, definitely a new network can be designed to be smart from the outset with the embedded information and the communication technologies. We need to have the information, and that information has to be passed or communicated to a different devices. Based on this information, some decisions have to be taken, and those decisions have to be again transmitted to, or those decisions have to be communicated to the different agents or different units to implement those decisions. Based on the implemented decisions, some information again need to be collected. So further, these decisions need to be adapted or changed or corrected. So all these things to happen, we need to design and build a new system. But the problem comes here. It needs a lot of money. It needs huge resources. Those resources, financial resources, human resources, and it takes a lot of time. So it is not so easy to build altogether a new system. However, these objectives can be met by converting the existing systems into smart. Let us say, as we discussed at the beginning, we are saying that the system has to have the self-awareness. Means I need to know the voltage current at a particular point. So wherever I wanted to know the voltage and the current, let me install a sensor there. And I need to communicate this voltage and the current to some control station. So let me build a communication network so that information can be transmitted from a particular node or from the load to the control station. Again, the decision can be taken at the control station, and those decisions may be communicated to the implementing agent, let us say controller, let us say a switch, an isolating switch, or a power electronic switch, or a static switch. So those information has to be passed. So by integrating this information and the communication technologies with the existing system, we can convert, or basically we are giving voice to the existing system. So we can convert those passive networks or the existing conventional networks into smart networks. So with this embedded information and the communication technologies, the existing networks can be converted, existing grid can be transformed into a smart electric grid. So earlier we are just operating in the mode of build and connect. So we are having the loads, we are building the generating stations, and we are connecting the generating stations to the loads. This is we are operating with the build and connect. Now, the new concept is let us connect every node and let us manage them wisely. Let us manage them intelligently. Let us manage them smartly. Okay. So we are moving from build and connect to connect and manage. All right. So I hope I'm clear. Any questions? Yes. Is there any question or any doubt? So is everything is the concept of smart grid is clear?
Yes, sir. Clear.
Fine. Thank you. Now, as I said, the traditional power grid, we are having, we are going to make the market operations. Basically, we can say that the economic dispatch, or we'll go for the optimal dispatch. How much amount of the generation we should get it from different generating plants or from the units, that is going to be decided. What is to be connected, what is to be disconnected, and what is the price, everything will be decided here. Thereafter we'll be having the generation units, thereafter we'll be having the transmission units. So here we are going to step up the voltage, so high voltage, then we are going to transmit it. So we are going to have step down here, so LV to the HVN here, and thereafter we are going to distribute the generated electricity to different loads. So as I mentioned earlier, we are having the unidirectional power flow, that is from the high voltage end to the low voltage end, one way flow of electricity. So we are having the centralized bulk generations, and the traditional systems are heavy reliance on the coal and the oil, and we are having the limited automation. Please understand, we may be getting a doubt that so why we are having the relays that works, we are having the circuit breaker that works. Yes, they are working and they will work, but please understand, we are having that automation is limited. I'm not saying that we do not have the automation in the existing system, but that automation is limited. I'm not saying that the awareness is not there to the system, because our circuit breakers are operating means based on the inputs from the relay, and how the relay is taking the decision based on the voltage or current or the frequency, whatever it is there. But this automation is limited, but the information that is available with the relays are limited. So we are having the limited automation and we are having the limited awareness, and unfortunately, though the consumer is the one who ultimately is going to get benefit, or ultimately who is going to get distress, or ultimately who is going to pay the money, he will be nowhere in the scene, or he is nowhere in the scene. The consumer lacks the data to manage his energy usage. If the electricity is there, means it is there. If it is not there, means it is not there. Even that is the case even today with many of the areas in Bangalore city. That's how it is as on today. Then what we are aspiring for? The smart grid is an electricity network with added ICT, information and the communication technologies. So this is our electricity network, and this is our communication network. Just like at every stage, we are having different units to operate. In communication network also, we are going to have different units to operate, right? And these two together can form a smart electric grid. Okay. And so far, we do not have the integration of the renewable energy sources, but in future, we are going to have the integration of the renewable energy sources. So not only that, the another element, electric vehicles, EVs. Many of the vehicles now are slowly, the transportation sector is also going to get getting transformed into the electric mobilities. So these new additions, the renewable energy sources and the electric vehicles are going to come. Along with that, we have to integrate the ICTs, information and communication technologies, with our power network in order to achieve the objectives of the smart grid. Okay, smart grid should be, just to summarize this particular definition is given by Indian Smart Grid Forum. So it should be fully automated power delivery network. We should be having two-way flow of electricity as well as the information. Please understand. and it should be more and more environment friendly. That is, it should be lower carbon footprint, and we should be having digital technologies. I'm talking about, how we are going to process the data, how we are going to take the decisions. So we should be having adoption of these digital technologies in the power network, and we should be having the improved power quality. We should not be having low voltage or high voltage, or we should not be having any kind of interruptions. Right, we are in the 21st century, so we should be having a grid that meets the aspirations of different stakeholders of 21st century, and we should be having reduced disruptions. We should be having improved efficiency, and we should be able to utilize the available assets to the best possible extent. So this is how a smart grid can be formed. So this is what, okay, as we have seen, this is generation, transmission, distribution, and these are our loads. Similarly, at the same level, we'll be having a wide area networks at the generation and the transmission. Thereafter, we'll be having the distribution substation networks, let us say hotspots. And in our loads, we may be having home area network, or building area, or business area network, or industrial area network, or the lands, local area networks. And these networks, both power network and the communication network, should be integrated. Okay, anyway, this slide, anyway, we have already have a discussion. Considering the time, I'm just skipping this. So a fully functioning smart grid is likely to require a radical overhaul of the existing commercial and regulatory relationships between distribution, supply, generation, and the transmission companies. So please understand, in order to achieve the smart grid, it is not only the equipment or the technology that we develop, but it requires a radical change. Please understand. Please note that it requires a radical change. Okay, radical change in the policies, commercial and regulatory relationship between distribution companies, supply, generation, and the transmission companies. Okay, so we need to have the policy changes are at most important. Unless otherwise, even though you build the technology, even though you cannot deploy the technology unless otherwise the regulation allows, and the regulation change will happen only when the policy changes are effective. Okay, and importantly, the consumer, as we know that, or even now also, many of us, if we just go to the villages, people are objecting for the digital meters. Forget about the smart meters. People are objecting for the digital meters. Now we have to move from the analog meters to the digital meters, even further digital meters to the smart meters, right? And this can happen only when the consumer is able to accept these changes. Okay, so let's hope things will be realized very soon. Now, coming to the microgrid. Now we are talking about the smart grid or smart electric grid. Now we are just moving on to the microgrid. So what is the relation between the smart grid and the microgrid? As we discussed earlier, 2 slides back, in order to build altogether a new system, which is a smart electric grid, it needs few resources. Let us say the financial resources, human resources, and consumes a lot of time. Even though we are okay with all these things, what we do with the existing systems? That is another question. So instead of going for altogether new system, or instead of building altogether a huge system, let us adopt these changes at the micro level, at the small level, not at the huge level or the bigger level. So let us have a microgrids, and let us inculcate these smart grid features in the microgrid. Once that is successfully implemented and realized, let us slowly connect these microgrids together so that we can form a bigger and bigger grid, ultimately the smart electric grid. All right, am I clear? Okay.
Yes, sir.
Yeah. Now, what is our understanding of microgrid? So anybody having any idea of the microgrid? Have you seen any microgrid? Have you seen any microgrid? None of you? Yes? All right, fine. Just before I answer this question, so let me just brief you what is a microgrid. Microgrid is basically a local power system that uses micro source generation, small generating units at the distribution level, means the low voltage, that caters to the local loads. So small sources at low voltage, and it is a localized power system. Power system means, of course, we need to have the generations and we should have loads, right? And these loads need to be connected with a network, distribution network. As it is a distribution network, the voltage level will be low. That's what a microgrid, a simple understanding of the microgrid. Microgrid, as its name suggests, a grid of smaller capacity when compared with the conventional grid. So we'll be having gigawatts of the power that is getting transmitted over a conventional grid. When it comes to the microgrid, in case of microgrid, it may be watts, sometimes it can be milliwatts, or it may go up to kilowatts. When compared with our conventional grid, the microgrid capacity is much smaller. Okay. It is having cluster of loads. It is having a cluster of loads, means group of loads, and micro sources, group of sources. So group of loads, group of sources operating as a single controllable entity. A single controllable entity means, what do you mean by single controllable entity? Yes. Though there are many loads are there, many generators may be there, but all these things together, they are going to operate as a single unit. Means, for example, one of the loads, there is increase. One of the loads is tapping little more amount of the power than earlier. In such case, one of the generators has to increase its power output, or one of the loads have decreased, or let us say disconnected. Then one of the generators, that generator can be any generator, it has to decrease its power output. So these loads and generators together, they will be operating as a single entity. A single entity means any change, any disturbance in any of these units, that should be compensated or complemented by any other element in the system. That what we call it as microgrid. But as it was mentioned, the amount of loads are small, means the sizes of the loads are small, the sizes of the generation is also small, and the network is a distributed network, that is LV network. Okay, so let us take two standard definitions. One is from the US Department of Energy and the one is the European Union's definition. So group of interconnected loads and DERs, distributed energy resources, within clearly defined electrical boundaries. I'll just talk about this electrical boundaries little later when I show the diagram. Or just to discuss this, we should be able to identify, distinguish, we should be able to differentiate what is grid and what is microgrid. What is the boundary of the grid, or what is the boundary between the microgrid and the grid. Okay, so a group of ERs within clearly defined electrical boundaries that acts as a single controllable entity, just now we have discussed, with respect to the grid. So when it comes to the grid, we should be able to see it separately. It is a separate entity, but it is not a single unit. It is a combination of multiple units, but operating together. That's what we call it as microgrid. Important thing is that many of us having a kind of a misconcept. Microgrid means, okay, it is nowhere in the grid, it is operating as a single entity. Please understand that it doesn't mean that it is operating in islanded. It is operating in isolated mode. No, not necessarily. So a microgrid can connect and disconnect. It may be operating in connection with the main grid. It may be operating in disconnection with the microgrid. If it is operating in connection with the microgrid, we'll call it as grid connected microgrid. If it is operating in disconnection, and there is no connection between the microgrid and the main grid, then we call it as islanded microgrid or isolated microgrid. Okay, that is the definition of US Department of Energy. Now coming to the definition of European Union's understanding, it is basically LV distribution network, the low voltage network with distributed energy resources and the storage devices. An important thing that European Union definition have considered the storage units also. So we may be having the generating sources, we may be having storage units also, and flexible loads. They are talking about the flexible loads. If you see that this definition is more of inclusive one when compared with the other definition. So the distribution network should be LV distribution network. We will be having multiple distributed energy resources, storage units, and flexible loads. We should be able to exercise the demand side management. And such systems can be operated both in non-autonomous and the autonomous way. Non-autonomous means so are autonomous. So Jain University is autonomous university or non-autonomous university? This call is
Autonomous only, sir.
autonomous.
That's why it is university.
Exactly. So then what is the difference between autonomous and non-autonomous? Because it is why I'm saying this. We are in this basically many of us are academicians, so we can understand this concept very easily. So what is the difference between a non-autonomous institution and the autonomous institution? Non-autonomous means affiliated, right? So when it comes to a non-autonomous institution, we just have to follow the instructions or the guidelines or rules and regulations that are defined by the university. All right. In the same manner, when the microgrid is operating in grid connection, when the microgrid is in non-autonomous mode, it has to follow the instructions of the grid. Means it has to maintain the voltage and the frequency of the grid. Wherever the interconnection is happening, it has to maintain the voltage, the same interconnection voltage. As it is getting interconnected with the grid, it has to maintain the same frequency of the grid. In addition to that, it has to supply the real and reactive powers, the power that are demanded by the grid or the system operator. So that's how the non-autonomous control works. That's how the non-autonomous microgrid has to operate. Coming to the autonomous way, as we know that autonomous, we will be having some flexibility. Means we can have our own examinations, we can have our own question papers, and we can have our own evaluation schemes. However, all these things are subject to the scrutiny of the university. Am I right? Or whatever it is, some authorities, let us say UGC or whatever it is there, or AICTE, whatever it is. So in this case, how it can be applied to a microgrid? It is something similar to that. Though we are operating as a microgrid, islanded microgrid or autonomous microgrid, though we are in the autonomous operation, though we have the flexibility to fix our voltage, operating voltage and the frequency, if the frequencies are deviating too much, the load performance will not be as desired. The loads are not going to perform as they are designed for. If the voltage deviations are too much from their nominal values, the power output or the work done will not be as desired or as for what they have been designed. So there is some regulation. So within that regulation, we will be having the flexibility. Am I clear? So we wanted to maintain the 50 Hz frequency. So we need not to maintain exactly the 50 Hz. Let us say 49.9 or 49. 49, 49.95 or 50.1, 50.2. We can maintain any value within that range. However, once you are operating in the non-autonomous mode, once you are operating in the grid connection mode, if the grid frequency is 50.1, you have to maintain 50.1. If the grid frequency is 49.9, you have to maintain 49.9 only. Even though within the microgrid, you have excess generation, you have sufficient generation, you cannot maintain any other frequency other than the grid frequency. Because you are operating in the grid connection mode. You are in the non-autonomous mode. Otherwise, the system stability will get affected. When compared with the grid, as the microgrid of smaller capacity, this effect will be more on the microgrid, but definitely it is going to affect the operation of your main grid as well. Am I clear? Okay. Yes. Any questions? The microgrid concept of the microgrid and autonomous and non-autonomous, are they clear or any questions?
Clear, sir.
Okay. I'm just listening only a few voices. Okay. As I mentioned, there are hundreds and more than 100 participants are there. So I wanted to listen from different people, at least for the next time.
Concept is very clear, sir.
Yes, sir. Yes, sir. Is
Thank
it clear? Is it clear?
Yeah. Thank you. Now, coming to a microgrid. Now, if you see, now we understood that what is a microgrid and what is a main grid. Now tell me, any one of you have seen the microgrid? One second. Yeah.
Hello,
So
sir.
yes. I'm just so you can raise the hand. That's why intentionally I have unshared the screen. Yeah. So any one of you have seen the microgrid? Please raise your hand.
Sir, actually, I have seen, sir, in our college, almost 50 kilowatt solar PV along with
Okay.
connection to main grid they have done, sir.
Very good, sir. Very good. What about others? Only one?
Yes, sir. In my college also there, sir. Solar power generation, 2 megawatt, I think.
Hello. Sir, are you there? Hello. Dear participants, am I audible?
You're audible, sir.
Yes, sir.
Yes, sir. You are audible, sir.
Okay. Thank you.
But
Yeah.
sir is not here, sir.
Yeah. I will just come
Yeah.
back.
I think I lost the connection for some time. Probably now I am audible.
Yes, sir. Please
Yeah.
proceed, sir.
Yeah. I'm just sharing the screen. Yeah, now it is visible. Slides are visible.
Yes, sir.
Yes, sir. Visual, sir.
Thank you. Yeah, now we understood what is a microgrid. So I just received only one response from one of the colleagues that he has seen the microgrid, but I just wanted to confirm that all of us are owners of microgrid, not for one microgrid, rather 2-3 microgrids. Sir, we are just using, most of us are using the laptop, right? So there is a battery, there is the source, and the monitor, the speakers, the microphone, or the fan, or your SMPS, your motherboard, all these are loads. Your keyboard, mouse, all these are loads. Isn't it, sir? Is it not? There is a source and there are loads, and they are interconnected and they are operating. Of course, it is a DC microgrid. Agree with me?
Yes, sir.
Yes, sir. Correct.
Now,
Yes,
when
sir.
we are connecting the charger, right? We are plugging
sir.
it into our sockets. So what is it?
Sockets. That is a AC charger. AC along with the DC output.
Yeah, it is basically grid connected microgrid. Isn't it?
Yes, sir. If we
Yes,
connect,
sir.
It may not be having all the features, but it qualifies for a microgrid. Our mobile phone, the
Okay,
battery
okay,
is there, right? We are using the earphones, we are using the screens, right? Multiple things. That is also microgrid. Okay, different features, but all these gadgets qualify for microgrids because there is a source, there is a load. The source, there is a connection between the source and the load. Sometimes we are going to charge, other time we are going to use these gadgets without any connection to the grid. So if it is getting charged and if you are using the device, it is basically grid connected microgrid. If got disconnected, if you are using purely on the battery, it is basically islanded microgrid, right? So are we not owners of the microgrids?
Yes, sir.
Yeah, thank you. Yeah. Now, when I'm discussing the definition of the microgrid, I said that there should be clearly defined electrical boundary. As you can see it here, okay, this is one case I'm seeing. So here, if you see, we are having, okay, the PV system is there, and there is a power electron converter that is connected here. Here also, a battery is there, battery bank, and there is a power electron converter, and there is a wind system. There are power electron converters, and we are having the multiple loads at different buses. And if you see, this is basically we are having the sources and we are having the loads. And these sources, PV, wind, and battery together, they are trying to supply the loads that are there, that are connected to them at different buses. So it qualifies for microgrid. And if this switch is closed, it is going to operate as grid connected microgrid. If this switch is open, this is basically autonomous microgrid, islanded microgrid. Is that clear?
Sir.
Yeah. Now moving on to that. So what we are expecting, what kind of operations that we are expecting, and what kind of control that we need to have it in the microgrid. Now we are just into the core of this particular talk, operations and the control. We just understood what you mean by smart grid and what is the significance of microgrid in the smart grid and what are the different operating modes and how to control it, that we'll see it. So in grid connected mode, the magnitude and the frequency of the DER system, that is distributed energy resource system, here we can see it as microgrid system. These are all imposed by the utility grid, as we have discussed. Now as we can see it here, we are connecting, let us say that we are connecting this microgrid with the grid. So when we are trying to connect this microgrid with the grid by closing the switch, this point voltage, wherever the interface is happening, it has to maintain the voltage that of the other side, the grid side point voltage, because we are just interfacing it. It has to maintain that voltage. In addition to that, as we are interfacing it, see, these two systems cannot operate at two different frequencies. So whatever the frequency of the grid is there, the same frequency we have to at the same frequency we have to operate our microgrid, because we are interfacing our microgrid with the grid. So this frequency and voltages are defined by the grid. That's why we are calling it as non-autonomous systems, grid connected operations, right? So as you can see it here, in grid connected mode, the magnitude and the frequency, voltage magnitude and the voltage frequency of the DER are imposed by the utility grid. The control task boiled down to, as the voltage and the frequency are decided by the grid, we will not be having any control over the voltage and the grid. Or so to say, our regulation does not allow to vary the voltage at the interconnection point. So the simple task is that your microgrid is connected to the grid. The voltage and the frequency are already fixed by the grid. In such case, at the max, what we can do? We can control, or we need to control the powers, that is real and reactive powers. Right? Means once the microgrid is connected with the grid, the voltage and the frequency are decided, and we need to regulate the real and reactive powers in the grid. So which amount of the real and reactive power has to flow or has to exchange between the grid and the microgrid? Please understand. Please understand. It is not again, we are going to, the microgrid is going to absorb from the main grid, or the microgrid is going to supply to the main grid. Not necessarily, based on the operating condition, based on our decision making. Whether we may be supplying the power to the grid, or we may be absorbing the power from the grid. So we will be having a control, or we need to control the real and reactive powers that are flowing in and out of the microgrid. That is the operation we need to achieve. Okay. So how we are going to achieve? We can have this operation can be achieved. We can use the current control mode, or we can use the voltage control mode. We can use the current control mode, or we can use the voltage control mode. As we have seen here, the system voltage is fixed. If the voltage is fixed, if at all I wanted to supply a certain amount of the real power or certain amount of the reactive power, I have to control the current that is flowing in and out of the microgrid. So that's what we can control the current. Or other words, this is basically, I'm talking about the simple basic understanding. Our real power P is equal to root 3 VLIL cos phi. Reactive power Q is equal to root 3 VLIL sin phi. The V is more or less fixed. So I we are going to vary. So based on that phi, the amount of the reactive power, the Q that flows in and out, we are going to vary. So it directly boils down to the control of the current. But I have mentioned here, we can go for either a current control mode, or we can go with the voltage control mode. Yes, we can control the voltage also here. How the voltage is? It is something like that. All of us have studied. Do you remember the power flow equation? That generally we study it in power system operation and control. What is the power flow equation? Okay, I'll just further brief it. So let us say this is our system. Okay, I'm saying, okay, this is our microgrid, switch that is closed, and this is our main grid on this side. So what is the amount of the power that flows between microgrid to the main grid? How do you know?
Sir, based on the voltage levels.
Only voltage level, sir, or anything else?
Reactance also.
Only that?
Reactance. See, power flow equation, sir, P is equal to
Yes,
E
sir.
into V by X sin delta.
Yes, sir. V1, V2. Let us say
Yes.
V1, V2 by X.
X into sin delta. Sir.
Assuming that X means it is basically our X by R ratio is large. So we are saying that V1, V2 by X into sin delta, right?
Correct, sir.
Okay. So what is this delta?
Delta is the power angle, sir.
The phase difference between this
V1
bus
and V2.
and the other bus, bus 1 and bus 2, or microgrid bus and the grid bus, right?
Yes, sir. Yes, sir.
Okay. So this is the amount of the real power that is flowing. So by controlling the delta, we can control the amount of real power that is flowing. Similarly, by controlling the magnitude of V1, V2, because I'm not going into the details because all of us knows this. So what is your Q? Q is proportional to, isn't it? Similar equation we can get it, right? It is basically V1 square minus V1 V2 by X cos delta, isn't it? Delta is small angle, right? So cos 0 would be 1. So V1 square by X, V1 V2 by X it is. So anyway, if you take the V1, the difference, V1 minus V2. So the magnitude difference between the two bus voltages will decide the amount of the reactive power flow. The phase difference between the two bus voltages will decide the amount of real power flow. Okay. So all of you will be able to recollect this fundamental.
Yes, sir.
Very good. Now, when it comes to the voltage strategy, means this is what we are going to control. We are going to control the voltage magnitudes, or we are going to control the phase difference between these voltages. Okay, that's what the voltage control strategy. Even if you want further details, I'll show something, we'll discuss something, but the fundamentally this is what it is. Yeah. So let us take the one operation that is basically grid connected mode operation. As we have discussed, the grid voltage and the frequency are fixed because it is a grid connected mode, non-autonomous mode. So we need to control only real and reactive powers, right? So what we do, so based on the economic dispatch, or based on the optimal dispatch, or based on the any other strategy. For example, I'm having a PV source. If I'm having a PV source, a renewable energy source, what amount of the power I should supply to the grid? What would be the amount of the power that I need to supply to the grid in general? Yes? Is it not maximum amount of the power? Whatever the maximum that is possible, isn't it? So I'm having a PV source, let us say, if I'm having a PV source or any other renewable energy source, so I try to supply the maximum amount of the power to the grid, to the rest of the system. So in such case, I'm going to define, okay, what is the maximum amount of the power that I can tap it from the renewable energy source, and I'm going to compare with it what is the exact amount that is flowing in, and my controller is going to decide the phase angle, just like the delta, what we are talking about here. Okay. And reactive power, as we have discussed, just now we have discussed the magnitudes. Magnitudes will decide the amount of the reactive power. So what is the reference reactive power and what is the actual reactive power? We'll be having a controller that gives the magnitude, at what voltage I should be maintaining. So I know I'm getting the magnitude, I know the phase, that will be decided based on the reactive power and the real power. Based on this, I'm going to generate the template, the voltage templates. If it is voltage template means three-phase systems, so three-phase voltage templates will be developed, references, VABCs, and I'm going to develop the PWM pulses, switching pulses based on different PWM schemes. We have studied, all of us have studied, even though you are from the power systems or you are from the power electronics or any other branch, all of us have studied the sinusoidal PWM. So we are going to generate the sinusoidal modulating signal, and we are going to have the carrier wave. So wherever we are having the crossovers, at that crossover points, we are going to generate the switching pulses, and our power electron converter will be fired as per the generated switching pulses. All right, is that clear, or any questions? Is that clear?
Yes, sir.
Yes, sir.
Yes,
So
sir.
this is basically, it is known as the direct power control, in which we are generating from the references of real and reactive powers, directly we are generating the voltage magnitudes and the phases. So can anybody tell me what is the disadvantage of this method? We are directly generating the voltages. As in the earlier slide, I have mentioned that we can control the means we can achieve this objective through current control, either by current control or by voltage control. What I have shown just now is direct voltage control method. So what is the disadvantage of this method? Yes, anybody?
Sir, harmonics.
No, sir, no. See, harmonics can be eliminated by having a proper modulation technique.
That source voltage may decrease, sir.
Sir, which voltage?
Source voltage will vary according to the load. As the load go on varies, source voltage also varies.
Not necessarily, sir, here, because we are having generally we'll be having a DC bus capacitor which stabilizes the source voltage.
Okay.
Here the problem is something like this. See, we are directly controlling the real and reactive powers. To achieve the real and reactive powers, we are generating the voltage references, right? But what about the current? It can be any value. At least during the transients, the current may go to higher value, which is going to damage the power electronic converter. Though you are achieving in steady state, you may be achieving the required values of real and reactive powers, but during the transients, the current values may shoot up, which is going to damage the power electronic converter switches. Okay, so that's why instead of going for a direct voltage control, we will be going with the current control method. That, as you can see it here, current control. So what we do, the same real and reactive power references will be there. Instead of generating the voltage references, we are going to generate the current references. That current references further will be utilized to generate the voltage references and the switching pulses. All right. This is the difference. The rest all is same. As you can see it here, due to current regulation provision, the VS is protected against the overvolts and the external faults, robust against the variations the parameters, and the system performance will be superior dynamic performance and high control precision, because we are going with the two-loop control or two-level control. This is all about the grid connected mode of microgrid. All right. And further, if you wanted to go for a renewable energy source, PV source, as we have mentioned, in case of PV source, we need to maintain the maximum possible power. We need to extract the maximum possible power from the system. So when you are saying that we need to extract the maximum possible power from the system, as we know that the PV systems, right? All of us know that we'll be having the PV characteristics, right? The power output of the PV system going to vary with respect to the operating voltage. So our objective is to operate here at this voltage such that we can extract the maximum possible power, that is equal to this. So we are going to define the VDC reference with the help of the maximum power point tracking algorithm, and we will control the voltage of the DC bus. Ultimately, we are controlling the PV source voltage, and using that we are going to generate the real and reactive power references. Further, these references will be utilized to generate the current references. These current references will be utilized to generate the switching pulses for the power electronic converter. So in this way, we can protect our power electronic converter from the transients. We can protect our switches from getting damaged. We can achieve the required amount of the real and reactive powers. However, this real power and reactive power, in case of the real power, we are going to define as per the maximum power point tracking algorithm. So in this way, we have to control the grid connected microgrid for the desired values of real and reactive powers. Any questions? All right.
No, sir.
So, sir, why ABC to DQ transformation is required, sir?
Sir, it is ABC to DQ transformation. If you see that, it is not necessary. The problem why we prefer the DQ transformation, it is because in case of ABC, we are having this is VA, VB, VC. It is basically three-phase signals, right? So they are time varying signals. So if you are having a time varying signal, normal PI controller, it is normal PI controller where your the PI gains are, if you see that we represent with KP plus K by S, right? So that is not going to work. It is because always your references are changing, because your references itself is time varying quantity. You are defining IA, IB, IC, which are time varying quantities. A normal PI controller will not be able to track this, because always you will be having that steady state error, which is resulting from time varying references. However, if you convert, if you are going with that ABC to DQ transformation, though in the ABC domain, they are time varying signals. When it comes to the DQ domain itself is synchronously rotating reference frame. So as our references are generated with the help of the synchronously rotating reference frame, our references, let us say ID reference or IQ reference or VD reference and VQ references, they are not time varying quantities. As they are not time varying quantities, a simple PI controller also will be able to track. Understood, sir? Is that clear?
Okay, sir. Clear.
Yes,
Sir.
two.
Means so non-linear quantities are transformed to linear quantities.
No, sir. It is, we cannot say like that. We can non-linear quantities. See, for example, we are saying that a resistor, a simple resistor, whose value is constant, right? The voltage is, let us say, Vm sin omega t. The current is Vm by R, Im sin omega t. So if you see that the R value is constant, as such there is no change in it. Because R is constant, Im sin omega t will be having the same value all the time. It is a linear value. It is not changing. But it is a time varying quantity. Your Im value, whatever you are saying, the Im value is constant, will be the same as long as your Vm is same, because your R value is same, right? But it is a time varying quantity.
Right.
There is the difference, please understand, sir, the difference between a nonlinear quantity and a time varying quantity. These two are different. Im sin omega t is a time varying quantity.
Okay, sir.
If Im is changing, Im itself is changing, then that not necessarily be a linear quantity.
Right.
Okay, sir. For example, your R values keep on changing.
No,
Then
yes.
I am also going to change. Right?
Okay, sir. Correct, sir.
So, yeah. When we go for the ABC to DQ transformation, we are just transforming the time varying quantities to a kind of time invariant quantities. Let us say a kind of some references, or some people will say that AC to DC quantity. But please understand a clear, just we need to understand it little more clear with clarity. They are ultimately AC quantities that we are representing without any time variation. As it doesn't have any time variation, people will say it as DC quantity. Okay. But it is just a transformation that appears to be what is the DC quantity? It is because not varying with respect to the time. However, it is appearing as a DC quantity. It is not varying with the time because of the transformation. The transformation had used the rotating reference frame, because the conversion that happens with the rotating reference frame. Because let us say ABC quantities are time changing, we are changing the reference frame also with respect to the same frequency as that of your the input quantity. Let us say I or V, whatever that is there, that is time varying. Just it is something like that, sir. We have even our old school days, when the two trains are running at the same speed, the relative speed is 0. They appears to be stationary. Is that clear, sir, now?
Yes,
Hopefully.
sir.
Exactly, that's what we do in this transformation. But relatively they are stationary, but for the third body, which is stationary, they are moving. Okay.
Right, sir.
Yeah.
Okay, thank you, sir.
Yeah. Thank you. Now this is about the grid connected operation. Now going to the islanded mode operation. Islanded mode operation. The microgrid may be islanded. It may be because of the faults. Maybe in the external grid there may be fault. If the external grid is faulty, as you can see it here earlier, as we have seen, there is some fault here. If there is some fault, why should I shut down my microgrid? I'm having the generators which can meet my requirement of the loads. Then why should I shut down my microgrid? So let me get disconnected from the main grid and let me serve the loads that are connected to my microgrid. All right. So the microgrid may be operating in islanded mode, maybe because of the faults, or sometimes we plan it. Let us say, okay, there is a maintenance. The grid is getting maintained. It is not a fault. Rather, intentionally we have disconnected. Right. So in such cases, the microgrid may be operating in the islanded mode. So as it is islanded mode, there is no grid. The voltage and the frequency are not defined by any grid. So we have to define the voltage and the frequency. Who has to define? The microgrid itself has to define the voltage and the frequency, and the microgrid itself is responsible for maintaining the voltage and the frequency within the microgrid. So the microgrid is responsible for maintaining the frequency because there is no host grid. In addition, it has to regulate the voltage in the microgrid. Not only that, it has to maintain the voltage, it has to maintain the frequency. In order to maintain the voltage and the frequency, it has to manage the real and reactive powers of different sources in the microgrid. All right, understood? For example, let us say I'm having 10 loads, I'm having 5 generators. So how the load of these 10 loads are getting shared among 5 generators? So the microgrid itself is responsible for sharing the load among different generators. Microgrid itself is responsible for maintaining the voltage and the frequency within the microgrid. Okay. Now, there are different ways of controlling the microgrid. We may be having something like the central controller, and the instructions of the central controller will be followed by different what we can say that different distributed controllers. Okay, or we can have different strategies such that without having any centralized controls, we can have decentralized approaches. So when you are having the centralized approaches, the decision will be taken centrally and that will be implemented at different local controllers. Whereas in case of distributed control strategy, or in case of decentralized control strategy, decisions will be taken together by different controllers that are sitting beside every generator or the load. Okay. In this case, as I have mentioned, the microgrid itself is responsible for maintaining the voltage and the frequency. So we are going to give the reference voltage and the reference frequency to the controller. And this controller measures the actual voltage and the frequency along with the currents, as we have discussed, right? We have to have a two loop controller. We should be able to control the voltage. We should be able to control the current also, so that the power electron converter that is getting interfaced will not get damaged. So the voltage and the frequency will be defined within the microgrid. So we are going to collect the information of the actual voltage and the frequency in the microgrid along with the current output of individual generator. So using this, we are going to generate the current references. We are going to generate the current references, as we can see it here. We can see it here, current references. Using the current references, we are going to generate the voltage references and the PWM signals. So except this part, the rest is same as that of the grid connected operation. The rest is same as that of the grid connected operation. In case of the grid connected operation, we are going to define the real and reactive power references here. I'm just going back to the slide just to make you understand. As you can see it here, we are going to define the real and reactive powers in case of the grid connected mode, because our voltage and the frequencies are already defined by the grid. In case of islanded operation, we have to maintain the voltage and the frequency. That's why we are defining the required amount of the voltage and the frequency. And we are going to compare with the what is the existing voltage and the frequency, and we are going to measure the currents. Based on these currents, we are going to decide the current references as per the power sharing. Rest all the same as that of the grid connected operation. Okay, so this is how we have to operate and control the microgrid for different modes of operation, whether it is a grid connected mode operation or it is an islanded mode operation. Sir, how much time I'm having from now?
Yeah, it is actually 9 o'clock is the closing time, sir. Maybe you can take 5 more minutes or 10 more minutes.
Okay, fine. I'll just discuss one important example quickly.
Sure, sir.
Okay. Yeah.
Okay.
So let us take a simple microgrid here. Okay. As you can see that we are having a PV system, PV generator, and I just wanted to have a heterogeneous sources. I do not want to take all the static interfaces. So I have taken a generator, a renewable energy source with a static interface, that is a power electron converter, and a diesel generator with a rotating machine interface, that is synchronous machine. And I'm having one static load, a simple RL load, as well as one rotating machine load, induction motor. And if the switch is closed, it is going to operate in grid connected mode. If the switch is open, it is going to operate in the autonomous mode, islanded mode, right? So a simple example, you can see it here. So when you are having this, so it is basically a grid connected mode operation. Okay, I'll just explain the importance or the significance of control, okay, of a microgrid in different modes. For example, in this case, it is operating in grid connected mode. As it is operating in the grid connected mode, this microgrid is having a generation. Let us say, initially the PV power output is something around 14 kilowatts. The diesel generator is delivering around 40 kilowatts. So together around 54 kilowatts generation is there. As you can see that the load is something around 21 kilowatts, minus 21. Please understand, load I have taken it as minus, the generation I have taken it as positive. So the load is means minus 21. So total load is 21 kilowatts. The generation is around 54 kilowatts. So what is that is left, sir? What is the leftover generation? Excess power in the microgrid. What is the excess power? 54 minus 21. 33, right? So around 33 kilowatts excess generation is there. So as it is operating in grid connected mode, so 33 kilowatts minus whatever the local losses are there, around 31 and 32 kilowatts are being fed to the grid. So as it is grid connected operation, whatever the variations that are happening in the generation, as long as the load is constant, they are going to reflect here in the grid feeding. So total generation minus load will be the grid feeding if the generation is excess. If the generation is deficit, it has to come from the grid. However, the frequency will be maintained at 50 Hz because it is a grid connected operation. All right. Here you can see it here. The PV generation became constant, right? But the diesel generator output has decreased. The load is constant in the microgrid. Hence, the grid feeding from the microgrid is decreasing. Beyond this, the PV generation is constant. Diesel generator is also, PV generation is constant. Diesel generation is also constant. But the load is varying. As the load is varying, the grid power is going to vary. For example, if the load is decreasing, means the negative means load is more and more negative, means load is increasing. As the load is increasing, grid power feeding is going to decrease. If the load is less negative, means the load is decreasing, So the grid power feeding is increasing. So in this way, the power is being balanced in the microgrid, and as it is operating in the grid connected mode, the frequency is maintained as constant here at the 50 Hz. This scenario is clear, I believe. Any doubts? All right. Now when we are having the, as we have discussed, there is a fault or when there is an isolation. I have considered a case here, as you can see it here, right? So here is the instant where our microgrid got islanded from the main grid. So when the microgrid got islanded from the main grid, as you can see it here, the grid feeding. So before the islanding, there is excess power of something around 24 kilowatts or to the tune of 25 kilowatts. So as there is excess power of 25 kilowatts, suddenly the microgrid got isolated. Before the isolation, these 25 kilowatts are flowing into the grid. Suddenly the breaker has opened. Suddenly the microgrid got islanded. So what will happen? So where this 25 kilowatts will go? Where it will go? Can it go to the grid? Yes. Can this power go to the grid? It cannot, because the microgrid, as you can see it here, the blue one, right? The power became zero. The grid power became zero. As the grid power became zero, however, there is an excess generation that is prevailing over there in the microgrid. Because there is an excess power that is prevailing over the microgrid, within the microgrid, the frequency of the system started rising. As you can see it here, within short time, because of the excess generation that is available in the microgrid, the frequency is shooting up. Not only the frequency, as you can see it here, the voltage is also going to get shooted up. Because of this, obviously the frequency is going high, the voltage is also going high, the relay starts operating. Once the relay starts operating, either some of the loads will get disconnected or some of the generations, here the generators will get disconnected. If the generator is getting disconnected, then there is a possibility that the system going to become unstable. Means what is happening? There is excess generation. Because of that excess generation, the frequency is going to get shooted up, and that is going to open the breaker and the system becomes unstable. Right? This is what it is going to happen with the microgrids which are operating in the grid connected mode, and before the isolation there is excess power that is there in the microgrid. Now what is to be done? We can go with the storages, but the storages, as we know that still the cost is very high, right? The problem is it's not the same as that of our traditional systems, because our traditional systems are conventional grids, many number of loads, and the system inertia is huge. However, when it comes to the microgrid, it is having very limited resources. Loads are less, we do not have any storage, and as the number of units are less, the inertia is less. Even for a small disturbance, even for, let us say, if you see within 100 megawatts, 1 kilowatt is nothing. Let us say within 10 kilowatts, 1 kilowatt is 10% difference. Even a small disturbance can create or can result in instability in the system. Okay, smaller systems, larger deviations. In case of conventional systems, we are having the synchronous generators which can control its power output. Right? So synchronous generators having the speed governors, they can regulate the power outputs. However, in case of the microgrids, mostly we are going to have the renewable energy sources, and they are interfaced with the power electronic converters, and they do not have any speed governors, or they do not have any frequency sensors, or moreover, in case of the microgrids, your frequency and the real power are not closely coupled. So we will be having a reducer support. And this is what the power electronic converters, there is no inertia support also. So ultimately the system is going to become unstable. The one thing that what we can do it in case of this renewable based microgrids is, so let us not go for the maximum power point tracking always. Let us try to go for a power balance when it is operating in the islanded mode. That is the significance of intelligent operation, right? So far we are discussing that let us operate at the maximum power point tracking, but maximum power point tracking may not be good always. We have to go for a power dispatch. We have to convert the existing renewable energy source into a dispatchable source. So we have to design a controller such that are going to operate as dispatchable sources. Okay, so as the time is limited, I'm just skipping this. The same system as we have discussed, the system became unstable. This is what the frequency is increasing, right? And the voltage is increasing. Relays will operate. Some of the units will get disconnected, and the system is going to become unstable. Now, what is to be done here? What can be done here? So we can have some intelligent controller. As we said, okay, so far we are operating at the maximum power point tracking here, and this is good when it is operating in the grid connection mode. When it is islanded mode, if you are operating at the maximum power point tracking, and if there is an excess generation in the microgrid, if you see the same microgrid, I have represented in different way. It is the same microgrid what we have discussed earlier. There is a PV source, okay, there is a diesel generator, there is an induction motor, and there is RL load. The same system I have represented in a different way, but it is the same microgrid as we have discussed earlier. The same microgrid. This is the same microgrid. All right. So we are not supposed to operate at the maximum power point always. Once the microgrid got isolated from the main grid, so we have to go for the power regulation. We have to convert this PV source into a dispatchable source such that the microgrid is able to maintain its voltage and the frequency stability. So once the microgrid got isolated from the main grid, the proper coordination, as you can see it here, proper coordination between the diesel generator and the PV is necessary to maintain the system stability. This is basically, I have developed a fuzzy controller because we are saying that we are going to operate at a decreased power output. We are not going to operate at this maximum power output. Not at this maximum power output. We just have to operate here at the decreased power output. So at what in order to regulate the power output, I have to control the operating voltage. So how to decide what should be my reference operating voltage such that the power will not be excess or power will not be deficit. It is just enough to meet the load such that the frequency and the voltage will be maintained constant. So for that, I have developed a fuzzy controller. This fuzzy controller is going to give the voltage reference. Beyond that, when I'm going to use the fuzzy controller, this is basically decides. It is basically a condition-based optimization, we can say. And beyond that, a intelligent controller that is working here. Here, if you see, if the frequency deviation is less than minus 0.05, please understand, positive delta F means frequency is less than the nominal value. Negative delta F means frequency is more than the nominal value. So the frequency is much less than 0.05 means there is an excess generation. The moment when there is an excess generation in the microgrid, among the PV and the diesel generator, which generator I should control? I should control the PV output or I should control the diesel generator output for the excess generation. I have excess generation in the microgrid. I want to decrease the power output. Which generator I should decrease?
Diesel generator.
Very good. Diesel generator only, because the unit cost is high and that is not environment friendly. So the moment when the frequency is high, when it is more and more negative, I have to control the diesel generator. Okay, when the Y is equal to 1, I have to control the diesel generator. Not only that, if the frequency is more than 0.05 means the frequency is decreasing. If the frequency is decreasing, I should increase the power output of the generator. So which generator I should increase? Which generator? Among the PV and the diesel? I wanted to increase the power output of the generator. PV. Very good. So if the frequency is less, then I should increase the power output of the PV generator. How long I can increase? I can go up to maximum power point, right? Beyond that, I cannot increase. That is my limit. So when the frequency is less than the nominal value, I should control the output of the PV generator, or more precisely, I should increase the power output of the PV generator. Once the PV generator reaches its maximum power output, if still the frequency is decreasing, then I should increase the diesel generator power output. Means if at all I wanted to decrease the power output of the generator for the increased frequency, I should control the diesel generator. If at all I wanted to increase the power output, my first preference is PV generator. If the PV generator is exhausted, it has already reached the maximum power output, then only I should be going with the diesel generator. On another case, when there is a negative frequency, means there is excess generation. In that case, I should see whether the PV generator has reached, diesel generator has reached its minimum value or not. Because my priority is to utilize the diesel generator to the minimum extent and to utilize the PV generator to the maximum extent. So immediately I should decrease the diesel generator. Once the diesel generator has reached its minimum value, then I should be decreasing the power output of the PV generator. So if you see, this typical problem has been solved using a kind of condition based optimization along with the intelligent controller that makes uses of the fuzzy controller. In addition to that, there is a ANN neural network that gives the information of the VDC at what is the maximum power point voltage. So the combination. So if you see, I have used the condition optimization, I have used the neural network, I have used a fuzzy controller. The optimization I have used, these conditions I have used to decide what is to be controlled. Neural network I have used to predict what is the maximum possible voltage. The fuzzy controller I have used to decide within that range at what voltage precisely I should operate my PV generator. So we have different tools, and we should know what tool we should use for the given purpose, for the given problem, and we have to have a coordination among these tools such that we should be able to control different units, let it be generators or the loads in the microgrid, such that we can achieve the system stability. Okay, just I'm showing some results. So this is the case as we can see it here. Here is the instant where as you can see that the grid feeding has become 0, but before the grid disconnection, there is a excess power that is flowing into the grid. You can see that around 20 kilowatts. So as there is excess generation, as we have seen in the earlier case, the system became unstable. Now the controller has to shift its mode to the islanded operation. Once it is into the islanded operation, as there is excess generation, immediately the diesel generator power output has been brought down to its minimum value. So in spite of that, as we can see it here, still we are having higher frequency, means still we are having excess power in the microgrid. So as the diesel generator has already reached its minimum value, we have to decrease the power output of the PV generator such that system frequency will be maintained 50 Hz. So if the load is increasing, as you can see it here, our first choice is PV power. We have to increase the output of the PV generator. For further increase, the PV generation has exhausted. It has reached the maximum possible value. As it has reached the maximum possible value, in order to maintain the balance of generation and the load, in order to maintain the system stability, I have to increase the power output of the diesel generator to meet the increased load, as we can see it here. Okay. However, the frequency will be, even though it is isolated, the frequency has been maintained at 50 Hz and the system is operating very stably, even in islanded operation. Okay. If the power outputs are changing, as we can see that grid power has become 0, this is the another case where before the islanding, the microgrid is absorbing the power from the main grid. That's why the power feeding to the main grid is negative. Means microgrid is absorbing power from the main grid. So once the microgrid got isolated from the main grid, there is a deficit. As there is a deficit, PV is already operating at MPP. In order to maintain the system stability, in order to protect the system stability, diesel generator has to increase its power output. So over the time, if the PV power output is increasing, in order to utilize the PV generator to the maximum possible extent, the diesel generator has to decrease its power output at the same pace, at the same rate as that of the PV generator power output. So we have to have a perfect coordination among multiple units in the microgrid such that the system stability can be achieved. Okay. Even in this case also, I could maintain the frequency stably at 50 Hz. System is stable. As such, there is no problem. Okay. So if we just continue, is basically an experimental verification that what we have done. So all these cases are verified. Even further, more concepts have been developed, and they have published some work in IEEE transactions. So like that, we can further develop the concepts, but however, the time is limited. So let me close this here. So now I am open to any questions. Yeah, if you have any questions, please.
Sir.
Yes, sir, please.
So in PV grid solar system, the frequencies actually depends on speed. How will you control the frequency in PV system?
Sir, please come again.
In the PV system, you need to control the frequency.
Yes.
See, usually the frequency depends on speed. Only in the with respect to rotating machines, synchronous machines, or diesel engine generators, like that. But in case of PV system, how the frequency and the speed relations?
Sir, in case of a PV system, please understand one thing. In case of a conventional system, see, there is a rotating machine, there is a rotating mass, and because of that inertia, you will be having a direct relation between your real power and the frequency. However, in case of a PV system, we are having a power electron converter. And this power electron converter, we are going to decide the frequency of the power electron converter, at what frequency we should control. Okay. As such, there is no if you are giving certain frequency, your machine is going to run at a speed that is decided by the frequency, the supply frequency. However, the power output does not have any effect on the operating frequency of the inverter. See, the same power output, let us say I'm just taking a synchronous machine, let us say synchronous generator. Okay, it is rated for, let us say, 100 megawatts. Okay, so at 100 megawatts, it is giving, let us say, 50 Hz. For example, if I'm trying to draw a little higher power output, 105 megawatts, then definitely the frequency is going to decrease. Okay, the frequency output is going to decrease, unless otherwise you are increasing the prime mover input. That comes under speed regulation and other things. However, we can clearly observe that if the power output of the generator is changing, then the frequency of the generator is going to change. But that is not true with the power electronic converter. It is because you are drawing, let us say you are having a 10 kilowatt inverter. A 10 kilowatt inverter, whether it is giving a 5 kilowatt or 15 kilowatts, its frequency may not change unless otherwise you change it. How you change it? With the PWM signals, with the carrier wave, with the modulating signal. You are going to change the modulating signal frequency. So based on the modulating signal frequency, the output frequency of the inverter is going to change. However, it can be of any power value. It can be 5 kilowatts, 15 kilowatts, or 10 kilowatts. Understood, sir? Is that clear?
Yes, sir. Means the switching frequency, by changing switching frequency, we can change the power frequency of the
Sir,
system.
please let me correct it. It is not the switching frequency, it is modulating frequency.
Switch modulation frequency.
Okay, sir. Not the carrier frequency, rather modulating wave frequency.
Okay, sir. Thank
Okay?
you, sir.
Yeah.
Thank you, sir.
Thank you. So any other question? Sir, I think I have one question. How can we effectively address the challenges of voltage and the frequency stability in islanding mode, especially dealing with high penetration of intermittent renewable energy sources like solar and wind? I think this is the case that I have shown at the end. You can let me go to that slide. So as you can see it here, the power outputs are varying. Okay, you can see my screen, right? Can you see my screen? No. Yeah. So the power outputs are varying. This is what point that we have discussed. Even though they are varying, this variation we have to, as per this variation, we have to control the other generator, other sources accordingly. And if that control is not possible from the source, we have to exercise the demand side management. However, it has to be controlled properly. Okay, that is what, in case of microgrids, the control will be having the paramount importance, and that is very critical and complex also. Okay, so any other question? I hope, am I clear, sir? I think Sri, yeah, I could not pronounce this name. Some Sri Shaina something.
Yeah, Sri Shaina, sir.
Yeah. So am I clear, sir? Okay. Yes?
Yes.
Yeah. Next question. How to control the reactive power in grid connected PV? This question also I have answered, sir. If you just, as we have discussed, when I have just represented with 2 buses, right? I just erased it. 2 buses, we have just, the real power V1, V2 by X into sine delta. The reactive power is proportional to, or it is equal to V1 into V1 minus V2 by X into cos delta. So the difference between the magnitudes of the voltages, by controlling it, let us say V1 minus V2 is positive, then Q is positive. If V1 minus V2 is positive large, your Q value will be large. If V1 minus V2 is negative, Q is negative. Q is negative means instead of supplying, you may be absorbing the reactive power from the grid. So by controlling the magnitudes, the relative magnitudes of 2 end voltages, we can control the reactive power. I think it is Yogesh. Sir, am I clear? Yogesh ji, am I clear? Is there? All right. I think Yogesh sir, are you there? Okay, fine.
Maybe he may not be there, sir.
That's okay. It's already 9:30. It's okay.
Yes, sir. Dear participants, please open your cameras. So we will take the photograph. Sir, please open the camera, sir. We will take
Yeah,
the
one more question, sir. Here, I think probably, yeah, this is two questions are there. Quickly, let me just go through it. So, what are the challenges of implementing intelligent systems in microgrid, particularly in terms of cybersecurity and interoperability, considering islanded and the connected mode? There are many challenges, sir. Right from the we will be having a protection challenge. So we'll be having this control challenge. What I have discussed. We'll be having the power dispatch challenge, and we'll be having, of course, the cybersecurity will be another challenge. But not there are many challenges. See, even the power voltage is a problem. For example, you are feeding the power, you are not absorbing the power. So the moment when you are trying to feed the power, the voltage levels are going to shoot up, and these are intermediate shoots ups are there. And this is not going to happen at one location; it is going to happen at the many locations. Like that, if you keep on discussing, there are many challenges that we need to address. And why we are not so far, why we are not concerned, it is because we do not have that much level of penetration of the renewable energy sources. The amount of renewable energy sources in our power system, the share even today it is very less, to the tune of 10%. So if it goes up, these challenges will be more and more critical, and they can destabilize the system, and we need to develop the solutions for these challenges. Okay, the next question: what percent of voltage is acceptable? Okay, sir, I think maybe Dr. Durga, you are there, sir?
Yes, sir.
Yeah. So what percent of voltage change is acceptable? This percentage depends on at what voltage level we are operating. Just for example, in general, at a distribution level, let us say 230 or 440 volts range, 10% is acceptable. Okay. And as the voltage levels are increasing, let us say 440 kV. 10% of 440 kV is 40 kV. It is too much. Okay. So as the voltage levels are, there is a standard, IEEE 1547 standard you can refer. And even we are having a grid code, which is developed or published by CEA. It is in the Gazette. We are having a grid code, Indian grid code is there. So there, these percentage values are defined, but as a whole, the percentage may vary from at the max 10%, and it may go up to 2% also. So if the voltage levels are increasing, the percentage value will be decreasing. Okay.
Okay, sir. Okay, sir.
Yeah. Thank you. So any questions? Fine.
Chandrasekhar, sir, please open your camera, sir. We will take the.
I have already opened, sir.
Dear participants, please open your camera. We will take the photographs and we will end the session. Thank you so much, dear participants.
Yeah, thank you. Thank you, everyone.
Thank you, sir. Thank you so much for your elaborated lecture, and it shows whatever you are doing, that's what you are discussing here. So thank you so much for exploring, for making us to explore your work, and you have shown your entire work. So I request all the participants to kindly utilize this service, and this is one contact from IIT Bhubaneswar. So I feel we can go ahead with many other projects also. Maybe you can join as research scholars, and maybe you can join as JRF or SRF under sir, and even we can also collaborate with sir. So it's very good thing from your end. So I feel very happy such that So thank you, sir. Thank you so much for your kind cooperation. So you immediately accepted our invitation, and we will definitely meet in the next event, sir. Thank you so much. So
Sure, sir. Thank you very much. And if you have any further questions or if you want any further more discussions, just write to me. My mail ID is there. Okay, just drop your mail. And but one request is that please, you know how the schedules will be. Please don't expect immediate response, but definitely within a day or two, definitely I will respond. Okay, please wait and give some time, and you definitely will be getting the response. Okay, so wish you all the best. Thank you very much.
thank you, sir. Thank you so much, dear participants. Thank you so much for your kind cooperation. Thank you so much. And this is the end of the first day 4, and I think everyone is getting the spreadsheet here. So Google form, you can please check it. If you find difficult, I will share once again. Please let me know. Very valuable session. Thank you so much. Yeah, so please fill the feedback forms, then only attendance will be taken care. And that's all. If any things are there, I will communicate through WhatsApp group. Okay, thank you so much. And whatever test we have conducted today, it is a practice test actually. So later I will take the real test also. Maybe as we have discussed, maybe today is 4th day. Tomorrow, end of tomorrow, I will go ahead with another test of 15 marks again. So already 15 marks I have given the test. I hope everyone has got your result and also corrected answers also. Okay, please prepare properly accordingly. So most probably questions may come from this or in the similar fashion. Okay, so thank you so much, and good night all of you. Thanks for your kind cooperation till date, and 2 more days are left out, and kindly give the same cooperation. And my sincere request would be, please fill the Google forms, then only your attendance will be taken care of. Okay, I don't want to share Google forms in WhatsApp groups, and I know if I share in WhatsApp group, nobody will come to these classes. So that's why I don't want to share in WhatsApp group. Kindly come here, take the things, and then fill the form and then get the certificate. Thank you so much, and good night all of you. This is the end of the day. Thank you so much.